You probably think of time as a gentle, flowing river. It's a comforting story, told by the steady tick-tock of clocks and the familiar grid of calendars. It's the soft pull of memory and the bright hope of what's next. We live our lives on its banks, certain of its forward flow, of one moment causing the next, as predictably as a dropped stone sends ripples across a pond. But what if I told you this certainty is an illusion? A convenient fiction our minds have built to make sense of the world. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Tonight, we're drifting away from that comfortable shore. We're going to journey to the universe's most violent and mysterious edges, to see where that river of time doesn't just bend, but shatters. We'll venture to places where past, present, and future get scrambled, where the steady rhythm of existence dissolves into a whirlwind of cosmic secrets that defy our reality. This journey will force us to question the most basic assumption of our lives. That time always marches forward. But what if that march isn't guaranteed? What if the river could run dry, or loop back on itself, or just stop? The biggest question we can ask isn't about space, but about its inseparable partner. What happens when time itself breaks? To even begin to find the answer, we first have to understand the time we think we know. The comforting illusion of our time. Our sense of time begins, not in the cosmos, but in our heads. Every morning, the world feels like a seamless flow of experiences, but it's our brain that slices this flow into seconds, minutes, and hours. The clock on your wall isn't just a machine. It's an anchor, a metronome our consciousness syncs with to create a feeling of order. Calendars build on this, giving our lives a story with beginnings, middles, and ends. But our inner experience of time is way more personal than any clock. Our minds stretch and compress it. Think back to a long summer afternoon from your childhood. It might feel like it lasted forever. That's because a young, curious brain, taking in tons of new information, records experiences with incredible density. Now, compare that to waiting in a boring line. The seconds drag. Boredom makes time feel slow because our minds, starved of anything interesting, turn their attention to time itself. Emotions are powerful time sculptors. Like standing before a thundering waterfall, can make the present moment feel like it's expanding. Fear, in a crisis, can stretch a single second into a slow-motion scene, giving your brain precious extra moments to process danger and react. And good feelings, powered by chemicals like dopamine, can make our internal clock speed up, which is why time flies when you're having fun. We are, by nature, mental time travelers. We rarely live just in the now. Our minds are constantly dancing between the past and the future. Memories aren't perfect recordings. They're stories we tell ourselves, shaded by our current mood. The future is a landscape we paint with our hopes and fears. This constant flitting between what was and what will be is why the present can feel so slippery. And why does it always move in one direction? Why does a cup fall and shatter, but we never see the shards leap back together? This is the arrow of time, and for us, it's all about a fundamental law of physics, the second law of thermodynamics. It says that in a closed system, like the universe, the total amount of disorder, or entropy, tends to increase. An unbroken egg is orderly low entropy. A scrambled egg is chaotic high entropy. The universe moves toward a future of higher entropy. Your brain builds its story of time based on this sequence of cause and effect, of increasing disorder. It's a predictable rule. But the universe doesn't always play by our rules. The gentle, forward-flowing river of time we experience is just one calm stream in a much wilder, cosmic ocean. And now, leaving the familiar behind, we're heading into the rapids. Our first stop takes us back about a century, to the mind of the man who first realized the river of time wasn't so constant. Albert Einstein. Einstein's revolution. The malleable river. For most of history, time was thought to be absolute. Isaac Newton saw it as a universal clock, ticking at the same rate for everyone, everywhere. A second on Earth was a second on Jupiter. It was simple, intuitive, and wrong. In 1905, Albert Einstein published his theory of special relativity and smashed that universal clock to bits. The whole theory was built on a wild idea. The speed of light in a vacuum is the same for everyone, no matter how fast they're moving. This has some truly bizarre consequences. Imagine you're on a train with a light clock. A beam of light bounces between two mirrors, one on the floor and one on the ceiling. From your perspective, the light travels a simple up and down path. Each round trip is one tick. Now, picture a friend standing on the platform as your train speeds by. To them, the light pulse doesn't just go up and down. Because the train is moving, the light has to travel a longer, diagonal path. And here's the key. Since the speed of light must be the same for both you and your friend, but your friend sees the light travel a longer distance, they have to conclude that your clock is ticking more slowly than theirs. This isn't a trick. It's a real thing called time dilation. The faster you move through space, the slower you move through time. The effect is tiny at everyday speeds. An astronaut on the International Space Station, after a 6-month mission, has aged only about 0.005 seconds less than everyone on the ground. But in a thought experiment, if you could travel at 99.5% of the speed of light for 5 years, you'd return to Earth having aged just those 5 years, while 50 years would have passed for everyone back home. You would have effectively traveled into their future. But Einstein wasn't done. 10 years later, in 1915, he gave us general relativity, which was even more mind-bending. He showed that time is not just relative to speed, but also to gravity. He told us to stop thinking of gravity as a force and start imagining it as a curve or a warp in the fabric of the universe itself, a fabric he called spacetime. Think of a bowling ball on a trampoline. It creates a deep dimple. A marble rolling nearby gets its path curved by that dimple, and it looks like it's being pulled toward the ball. This is gravity. Mass tells space-time how to curve, and that curve tells matter how to move. But it's not just space that curves. Time does, too. The deeper you are in a gravitational well, the closer you are to something massive like a planet, the slower time flows. A clock at sea level will tick just a tiny bit slower than a clock on a mountaintop. This effect is crucial for technology. The satellites in our GPS network are in a weaker gravitational field, so their internal clocks run faster by about 45 microseconds every day. When combined with the 7 microsecond slowdown from their high speed, engineers have to program the satellites to correct for a net 38 microsecond gain each day. Without accounting for Einstein's theories, your GPS would be off by miles within a single day. So, time isn't a rigid metronome. It's a flexible river that can be stretched and squeezed by speed and gravity. Our life on a slow-moving planet, far from any extreme gravity, fools us into thinking the flow is constant. But what happens if we follow this river to a place where the current becomes impossibly strong? What happens if we head towards an object so massive that the dimple in space-time becomes a bottomless pit? This is where our ideas about time really start to fall apart. This is where we find a black hole. The first breaking point. The edge of a black hole. Black holes are gravity's ultimate show of force. They're what's left when a massive star collapses under its own weight, crushing a huge amount of matter into a point called a singularity. Around this singularity is a boundary of no return, the event horizon. It's not a solid surface, but a line in spacetime where gravity is so strong that nothing, not even light, can escape. It's here that our concept of time shatters. To get what's happening, let's imagine two people. Stella, a distant observer watching safely from her spaceship, and Alex, a brave astronaut falling into the black hole. From Stella's point of view, as Alex nears the event horizon, things get weird. The intense gravity makes time in Alex's frame of reference slow to a crawl relative to hers. As he gets closer and closer, his movements seem to slow down. The light from his ship gets stretched into longer, redder wavelengths, a process called gravitational redshift. To Stella, he would appear redder, dimmer, and slower. Until, right at the edge of the event horizon, he would seem to freeze entirely. From her perspective, Alex's time has stopped. She would watch him hover at the boundary, frozen for eternity, never actually crossing in. But what about Alex? For him, nothing special happens at the event horizon. His own clock ticks normally. He feels no jolt, sees no boundary. He sails smoothly across the horizon in a finite amount of his own time, having no idea that to the rest of the universe, he's a frozen image locked at the edge of infinity. This isn't a contradiction. It's a core consequence of relativity. Both realities are true in their own reference frames. For Stella, Alex is a permanent fixture. For Alex, he's inside the black hole. Once inside, Alex's fate is sealed. But here, the roles of space and time themselves get twisted. Outside the black hole, you can move any way you want in space, but you're forced to move forward in time. Inside, that's reversed. The singularity is no longer a place in space, but a moment in the future. All paths now lead to the singularity. You can no more avoid hitting it than you could avoid next Tuesday. As Alex gets closer to the center, the tidal forces become extreme, a process nicknamed spaghettification. But some ideas suggest that in his final plunge, time dilation could become so intense that what feels like seconds to him could correspond to billions or even trillions of years passing in the outside universe. In his last moments, he might witness the entire future of the cosmos flash before his eyes. And at the singularity itself? Here, our laws of physics, including Einstein's theories, break down. The math predicts a point of infinite density where the curvature of spacetime becomes infinite. At this point, the very concept of time ceases to exist. It's not that time stops, it's that the idea of before and after has no meaning. This is the first place where our understanding of time truly fails us. The edge of a black hole shows us that time is observer-dependent. It can freeze for one person while flowing normally for another. But what if we zoom in, way smaller than an atom, to a place where a different set of rules takes over? What happens to time in the weird, probabilistic world of quantum mechanics? The quantum realm. Time in tatters. For decades, physics has been ruled by two amazing but incompatible theories. General relativity describes the big stuff, planets, stars, and galaxies. Quantum mechanics governs the tiny stuff, atoms and electrons. The clash between them is known as the problem of time. In relativity, time is dynamic, a part of the spacetime fabric. But in quantum mechanics, time is treated as a fixed, absolute background, more like Newton's old idea. When physicists try to merge the two theories, a strange thing often happens to time. It vanishes from the equations. The most famous example is the Wheeler-DeWitt equation, an attempt at a quantum theory of gravity. Applied to the whole universe, it suggests a static, timeless reality. This has led some physicists to a wild conclusion. Maybe at the most fundamental level, time doesn't exist at all. So if time isn't fundamental, where does the flow we experience come from? One mind-bending idea is that time is an asterisk emergent phenomenon, born from something deeper: quantum entanglement. Entanglement is one of quantum mechanics' spookiest features, where two particles become linked so their fates are intertwined, no matter how far apart they are. The Page-Wouters mechanism, proposed in 1983, suggests that time itself emerges from this spooky connection. The idea is that the universe as a whole is static, but for an observer inside the universe, we can separate things into a clock and the rest. When the clock is entangled with the system appears to evolve from the clock's point of view. Time, in this view, is the relationship, the entanglement between different parts of the universe. Some small-scale lab experiments have demonstrated how this principle could work, showing that for internal observers of an entangled system, time does seem to emerge, while it's absent for external observers. This suggests our perception of a flowing river of time might be a consequence of our quantum point of view. We aren't just watching the universe go by. We are entangled with it, and this entanglement could be what creates our experience of time. Another quantum idea tears at the smooth fabric of time. What if time isn't continuous, but is made of tiny, indivisible ticks? Some physicists propose that time could be quantized, with each tick lasting for an unfathomably small duration known as Planck time. In this speculative picture, the smooth flow we experience is an illusion, like a movie that's really just a rapid series of still frames. At this quantum level, cause and effect might get fuzzy. Some speculative theories suggest quantum phenomena at this scale could be what gives time its direction, but the mainstream view still attributes the arrow of time to the low-entropy state of the early universe. The quantum realm presents us with a radical new picture. Time might not be fundamental. It could be an emergent property of entanglement, or a pixelated sequence. The river of time dissolves into a misty, uncertain quantum foam. But if time is so strange at the smallest scales, what does that say about its very beginning? Was there a before the Big Bang? The beginning of time? Was there a before? Our journey now takes us to the ultimate temporal boundary, the beginning of everything. The Big Bang theory describes a universe that started in an incredibly hot, dense state and has been expanding and cooling ever since. If you trace this expansion backward using classical relativity, you hit a singularity. Just like at the center of a black hole, our equations predict a point of infinite density where the laws of physics break down. This doesn't necessarily mean there was a literal point, but rather that our current theories are incomplete. If time itself began with the Big Bang, then asking what happened before is a meaningless question. It's like asking what's north of the North Pole. There's no before for anything to happen in. This idea of a hard beginning has always been a bit unsettling. It motivated Stephen Hawking and James Hartle to propose something even more profound, the no boundary proposal. This idea uses the language of quantum mechanics to describe the universe's origin. Hawking and Hartle suggested that to understand the universe's origin, we have to sum up all possible spacetime geometries that could lead to the universe we see today. In doing so, they used a mathematical tool called imaginary time. In this model, very close to the Big Bang, the distinction between time and space dissolves. Time behaves like another dimension of space. Hawking used a brilliant analogy. The surface of the Earth is finite, but it has no boundary or edge. The South Pole is a point on Earth, but it's not a beginning. It's just a place where the rules of direction change. Hawking proposed the early universe was like this. If you could go back in real time, you'd hit the Big Bang. But in imaginary time, there's no beginning. The universe would have smoothly emerged from a point of zero size, just like the lines of longitude emerge from the South Pole. According to this proposal, the universe is a completely self-contained system. It doesn't need a cause or a moment of creation because it has no beginning edge. It simply is. While the no-boundary proposal is a speculative and debated idea, it offers an elegant vision for how time itself might have begun. From this extraordinary beginning, our journey now leads to the other end of the timeline. What happens when the river of time reaches its ultimate destination? The end of time. The river runs dry. Cosmology offers several possible scenarios for the end of time. The universe's fate depends on a cosmic tug-of-war between gravity, trying to pull everything back together, and dark energy, which is making the expansion speed up. For a while, a possible ending was the Big Crunch. In this scenario, gravity would eventually win. The expansion would stop, and the universe would collapse back in on itself, ending in a final singularity. However, our current observations show that the expansion is accelerating, making this scenario unlikely. This leads us to the most widely accepted scenario: the heat death, or the Big Freeze. Here, the accelerating expansion continues forever. Galaxies will recede from one another until the night sky is almost completely dark. Stars will burn out, leaving behind a graveyard of cold remnants. The universe will become a vast, cold, dark, and nearly empty place. Over unimaginable timescales, even these remnants will decay. Eventually, the universe will approach a state of maximum entropy, a perfect equilibrium where everything is spread out uniformly at a temperature just above absolute zero. In this state, nothing really happens. With no energy gradients to drive processes, meaningful change would cease. The thermodynamic arrow of time, which relies on the increase of entropy, would become imperceptible. The river of time would become a perfectly still, frozen lake. The story of the cosmos would be over. But there is a more violent, though highly speculative, possibility called the Big Rip. This depends on the nature of dark energy. If it's a phantom energy that grows stronger over time, the cosmic acceleration would become unstoppable. In the final moments of a Big Rip, the expansion would become so powerful it would overcome all other forces. Clusters of galaxies, then galaxies themselves, would be torn apart. In the last seconds, stars, planets, and even atoms would be ripped to shreds. The finale is the tearing of spacetime itself. The very fabric of reality would be shredded. In this scenario, the river wouldn't just freeze. The very concept of a river would be annihilated. Whether our universe is destined for a slow freeze or a violent rip, the conclusion is similar. The familiar, flowing time we cherish is a temporary feature of our cosmic era. It had a beginning, and it will, in some form, have an end. We started on the calm banks of a river, our everyday perception of time. We saw it as a steady current carrying us from past to future. But our voyage has shown us the truth. That river is a wild and mysterious force. We've seen how Einstein's relativity shows that speed and gravity can change its flow. We journeyed to a black hole, where time can seem to freeze for one observer while flowing normally for another. We dove into the quantum foam, where the river may dissolve into a mist of probability, perhaps an illusion born of entanglement. We traveled to the very beginning, where some ideas suggest the river emerged gracefully as spacetime itself curved into existence. And we looked to the far future, where the river will either freeze in a heat death or be torn apart in a big rip. Time is not the simple story we tell ourselves. It breaks, it bends, it emerges, and it may one day end. We are born into this river, and we live our lives on its currents. But to look at the stars is to realize we are part of something far grander and stranger than we can ever fully grasp. This leaves us with one last question. If time is so deeply woven into our gravity, our speed, and our very entanglement with the world, then what does that say about consciousness itself? Are we just passive observers of this cosmic river, or is our perception somehow helping to chart its course? What do you think? Let me know your thoughts on time and reality in the comments below. And if this journey expanded your sense of the cosmos, please consider liking this video and subscribing for more explorations into the biggest questions in the universe. For a moment, imagine yourself floating far above the Earth. Not in a spacecraft with humming engines or glowing control panels. Just drifting silently, as if gravity has forgotten about you. Below, the blue curve of our planet slowly rotates beneath a thin veil of clouds. Cities glow faintly on the night side like scattered embers, while the sunlit half shines with oceans and continents that have existed for billions of years. From this distance, the Earth feels complete, whole, self-contained. And yet, if you keep drifting upward, something strange begins to happen. The planet becomes smaller. The moon slides quietly past you. Soon the entire Earth-Moon system looks like nothing more than a pale blue marble suspended in darkness. Continue drifting further still, and even the sun becomes just another bright star among many. At some point, a question begins to form in your mind. Where exactly does the universe end? It sounds like a simple question. Almost childish, the kind of thing someone might ask while staring at the night sky on a quiet evening. But the deeper you think about it, the stranger it becomes. Because every time humanity has tried to imagine the edge of the universe, we run into a strange problem. Not a technical limitation, not a missing telescope, but something much deeper. The problem is this. The universe may not have an edge at all. Not a wall. Not a boundary. Not even a distant horizon where everything simply stops. Instead, the universe appears to behave in a way that almost defies our everyday intuition. It might be endless. But not in the way most people imagine. When we think of something infinite, we usually picture a straight line that keeps going forever. A road stretching across an empty desert, disappearing into the distance with no final destination. But the universe might be infinite in a completely different way. To understand this, imagine something much simpler. Picture the surface of the Earth. Stand anywhere on the planet and start walking in a straight line. Walk long enough and eventually you will circle the globe and arrive back where you started. From your perspective on the ground, the Earth feels flat. Your path always seems to go forward. Yet the surface itself is curved. The Earth has no edge on its surface. There is no place where the ground suddenly stops and drops into nothingness. You can travel forever without ever reaching a boundary. Now imagine that idea, but expanded into 3 dimensions. Instead of a curved surface, imagine a curved space. This concept might sound abstract, but it is actually a very real possibility in cosmology. According to modern physics, space itself can be curved. Not curved into something else, but curved within its own geometry. This was one of the most profound insights of Einstein's theory of general relativity. Space is not just an empty stage where the universe happens. Space is dynamic, flexible, able to stretch and bend under the influence of energy and gravity. When massive objects like stars and galaxies exist, they don't simply sit inside space. They actually reshape the structure of space around them. And if space can bend locally, there is no reason it cannot bend on cosmic scales as well. Which brings us back to the question of the universe's edge. If space curves back onto itself, much like the surface of a sphere, then traveling forever in one direction might not lead you to an edge. Instead, you might eventually return to where you began. In other words, the universe could be finite, yet still have no boundary. This idea feels strange because our everyday experiences are built around objects that have clear edges. A table has edges. A room has walls. Even the Earth, if you dig downward, eventually has a boundary where solid rock meets the atmosphere above. But space itself might not behave like ordinary objects. It might be more like the surface of the Earth. complete and self-contained, but without a visible border. When cosmologists talk about the possible shape of the universe, they often describe three general possibilities. The first is a closed universe, where space curves back on itself like the surface of a sphere. The second is a flat universe, where space continues infinitely without curvature. And the third is an open universe, where space expands outward forever with a subtle negative curvature. Current measurements from missions like the Planck satellite suggest that the universe is extremely close to flat. But close to flat does not necessarily mean perfectly flat. And even a tiny curvature on cosmic scales could produce a universe so vast that its true shape remains beyond our observational limits. Because there is another complication. Even if the universe does have an edge somewhere, we may never be able to see it. Not because our telescopes are weak, but because of the finite speed of light. Light travels fast, incredibly fast, about 300,000 kilometers per second. But the universe itself is about 13.8 billion years old. That means the farthest distance light could have traveled since the beginning of the universe defines what we call the observable universe. Everything beyond that distance exists in principle. But its light has not had enough time to reach us yet. So when we look into the night sky, we are not seeing the entire universe. We are seeing only a small bubble around us. A sphere of visibility expanding slowly with time. The true universe beyond that bubble could be vastly larger. Perhaps unimaginably larger. Some cosmologists estimate that the total universe could be at least hundreds of times bigger than the observable region. Others suggest it may be effectively infinite. And if that is true, then the idea of reaching the edge of the universe becomes something like trying to walk to the end of the horizon. No matter how far you travel, the horizon always moves away. It is not a place you can reach. It is simply the limit of what you can see. And in a quiet way, this realization changes how we think about our place in the cosmos. Because the universe we observe, the billions of galaxies, the enormous clusters, the vast webs of cosmic structure, might be only a tiny fragment of something far larger. A small illuminated patch inside an ocean of space that extends far beyond our ability to explore. And somewhere out there, beyond the limits of our cosmic horizon, the universe may continue in ways we can barely imagine. Now imagine something even stranger. Suppose you could somehow build a spacecraft capable of traveling forever. Not just for decades or centuries, but for millions of years. A vessel powered by an engine that never fails, carrying explorers willing to drift across the vast emptiness of intergalactic space. You leave Earth behind. The planets fade into the distance. The sun shrinks into a bright star. Soon the familiar constellations dissolve as your perspective shifts among the stars of the Milky Way. After thousands of years of travel, the entire galaxy becomes a faint spiral of light behind you. Ahead lies only darkness, scattered with distant galaxies glowing like faint islands across an ocean of black. You keep traveling. Millions of years pass. You cross the enormous voids between galaxy clusters, regions of space so empty that a single galaxy might be separated from its neighbors by tens of millions of light years. These voids are among the largest structures in the universe. Silent cosmic deserts where almost nothing exists. Eventually you approach another galaxy. From far away it looks like a soft blur of light, but as you move closer, billions of stars slowly resolve into a magnificent spiral structure, glowing with the same quiet beauty as our own Milky Way. If intelligent life exists there, its inhabitants may also look out into the sky and wonder the same thing we do. Where does the universe end? But here is the strange part. No matter how far your spacecraft travels, no matter how many galaxies you pass, there would be no sign that you were approaching some ultimate boundary. No cosmic wall. No final curtain where the universe simply stops. Instead, every direction would look roughly the same. Galaxies scattered across the darkness. Clusters of galaxies forming enormous filaments stretching across hundreds of millions of light years. Vast empty voids between them. This pattern, known as the cosmic web, is one of the largest structures known to exist. If you could see the universe from far enough away, it would look almost like a gigantic neural network or a web of glowing threads suspended across space. Along these threads sit galaxies, clusters, and superclusters, all connected by gravity. Between them lie immense regions of emptiness. And yet even this enormous cosmic web might be only a small portion of a much larger structure. Because something remarkable happened about 13.8 billion years ago. The universe began expanding. Not like an explosion in space, but as an expansion of space itself. To picture this, imagine a loaf of raisin bread baking in an oven. As the dough expands, every raisin moves away from every other raisin. Not because the raisins themselves are moving through the dough, but because the dough between them is stretching. The universe behaves in a similar way. Galaxies are like raisins embedded within the expanding fabric of space. As space expands, galaxies drift further apart. This discovery was made in the 1920s by astronomer Edwin Hubble, who noticed something peculiar when observing distant galaxies. Their light was shifted toward the red end of the spectrum. This effect, called redshift, occurs when light waves stretch as the object emitting them moves away from us. The farther away a galaxy was, the faster it appeared to be receding. The conclusion was astonishing. The universe itself is expanding. And if we reverse that expansion in our minds, running the cosmic movie backward, everything would eventually converge toward an incredibly hot, dense state. What we now call the Big Bang. But the expansion of the universe leads to another strange consequence. It creates a horizon. Not a physical edge, but a limit to what we can observe. Because while space is expanding, light still travels at a finite speed. Even after billions of years, light from extremely distant regions may simply not have had enough time to reach us. Imagine standing in the middle of a vast foggy landscape. Your visibility is limited not because the land ends beyond the fog, but because your vision cannot penetrate any further. The observable universe is something like that foggy horizon. It defines the region from which light has had enough time to arrive since the beginning of cosmic expansion. Today, that observable sphere has a radius of roughly 46 billion light years. Which means the full diameter of the observable universe is about 93 billion light years across. And yet the universe itself could be vastly larger. Possibly hundreds, thousands, or even infinitely larger than what we can see. This means there may be entire regions of the cosmos forever hidden from us. Galaxies whose light will never reach Earth. Civilizations that might exist somewhere beyond our cosmic horizon, forever separated by the expanding fabric of space. It's a quiet and humbling thought. Even though our telescopes can peer billions of years into the past, we may only be seeing a tiny fragment of the whole universe. And the deeper we look, the stranger it becomes. Because the expansion of the universe is not slowing down. It is speeding up. In 1998, astronomers studying distant supernovae made a discovery that completely shocked the scientific world. Instead of gravity gradually slowing the expansion of the universe, something was pushing it faster and faster. The galaxies were accelerating away from each other. No one expected this. To explain it, scientists proposed the existence of a mysterious phenomenon called dark energy. Dark energy appears to fill all of space and acts like a kind of anti-gravity, causing the expansion of the universe to accelerate. Today, dark energy is believed to make up about 68% of the total energy in the universe. Yet we still do not know what it actually is. But its presence has a profound consequence. If the acceleration continues, more and more galaxies will eventually drift beyond our observable horizon. In the distant future, tens of billions of years from now, the night sky may look very different. Most galaxies outside our local group will disappear from view. Their light will stretch and fade as they move beyond the limits of observation. Future civilizations might look into the sky and see only a handful of nearby galaxies. They may never realize that the universe was once filled with countless others. The cosmic web would become invisible. The universe would appear small and lonely. And the evidence of the Big Bang itself might become impossible to detect. In a strange twist of cosmic timing, we happen to live in one of the few eras in the history of the universe where its true structure can still be observed. Where we can still see far enough into the darkness to piece together the story of how everything began. And yet, even with our most powerful telescopes and deepest theories, the original question still remains unanswered. Does the universe actually end? Or does it continue forever, far beyond the faint horizon of the observable cosmos? The deeper we explore, the more it seems that the idea of an edge may be something our minds invented. A concept shaped by everyday experience. Because in the strange geometry of the cosmos, the universe may not need an edge at all. It may simply continue quietly, endlessly, in every direction. To understand why the universe might not have an edge, it helps to imagine a world much simpler than our own. Picture a tiny civilization living on the surface of a vast sphere. These creatures are perfectly intelligent. They build cities, construct telescopes, and develop mathematics. But there is one limitation. They can only perceive 2 dimensions. For them, the world is a flat surface stretching in every direction. They do not experience up or down. Those dimensions are invisible to them. Their entire universe exists only across the curved surface they inhabit. If one of these explorers begins traveling in a straight line, something curious happens. At first, everything feels ordinary. The ground stretches endlessly ahead. The horizon remains distant and unreachable. But if the explorer continues long enough, eventually they will return to the exact place where they started. To them, this would be a profound mystery. They never turned around. They never encountered a boundary. There was no wall or edge. And yet their journey formed a complete loop. The reason, of course, is that their world is curved. The surface of a sphere has no edges, yet it is still finite. There is only a limited amount of surface area, even though travelers can wander forever without encountering a boundary. Cosmologists sometimes use this analogy to describe how our universe might behave. If space itself has a similar kind of curvature, not in 2 dimensions, but in 3, then the universe could also be finite without having an edge. In this scenario, traveling far enough in one direction might eventually bring you back to your starting point. But the scale would be unimaginably large. The observable universe alone spans tens of billions of light years. If the entire universe wraps around in some higher dimensional curvature, the full cosmic distance required to complete such a journey could be vastly greater. So large that even light, traveling for billions of years, has not yet had time to circle it. To our observations, the universe would appear endless. And perhaps it is. But modern cosmology leaves room for both possibilities. The universe may be infinite. Or it may be finite but unbounded. Both ideas are mathematically consistent with what we observe. What makes the question so difficult is that we are limited by the horizon of the observable universe. No matter how powerful our telescopes become, we cannot directly observe regions whose light has not yet reached us. It is a fundamental limit imposed by the age of the cosmos and the speed of light. And so the true shape of the universe may remain one of the deepest mysteries in science. But there is something even more fascinating hidden within this idea. Because the absence of an edge suggests that the universe might not behave like an ordinary object at all. When we think about objects, we imagine things that exist within space. A planet floats through space. A star occupies a location inside space. Even a galaxy cluster exists somewhere within the cosmic landscape. But the universe itself is not inside anything. There is no external room where the universe is sitting. There is no outer space beyond space. Instead, space itself is the structure that defines the universe. It is the fabric within which everything exists. Asking what lies outside the universe may be a little like asking what lies north of the North Pole. The question itself assumes a direction that no longer exists. This realization can feel unsettling at first. Our minds naturally search for boundaries. We expect every system to have an outside. A box has walls. A country has borders. Even oceans eventually meet land. But the universe may be the one thing that does not follow this rule. It may simply be all that exists. A self-contained structure of space, time, energy, and matter. And within that structure, everything unfolds. Galaxies form. Stars ignite. Planets cool. Life emerges. Civilizations look upward and begin asking questions about where it all ends. Yet the deeper we investigate, the more the universe seems to resist simple answers. The concept of an edge slowly dissolves. Not because we have not found it yet, but because the geometry of space may not allow such a thing to exist. Instead of an edge, we encounter horizons. Limits of observation rather than limits of existence. Beyond those horizons, the universe may continue quietly, carrying on its cosmic evolution in regions forever hidden from our view. More galaxies forming. More stars burning. More worlds perhaps orbiting distant suns. All unfolding within the same vast cosmic fabric. And when we step back and consider the full scale of this possibility, something remarkable emerges. Our tiny planet, orbiting a single star within one galaxy among hundreds of billions, is embedded within a universe that may stretch far beyond anything we will ever observe. The night sky, which already appears impossibly large, might represent only a small window into something vastly greater. An ocean of space whose true size remains unknown. And perhaps unknowable. But the mystery of the universe's edge leads naturally to another, even stranger question. If space itself can stretch, bend, and curve, what about time? Does time also extend endlessly in the same way? Or could time itself have boundaries? Places where the familiar flow of past, present, and future begins to break down. Because as physicists began to explore the deepest laws of the cosmos, they discovered something unexpected. Time is not as simple as it seems. In fact, in some regions of the universe, the very idea of before and after may begin to lose its meaning. And it is there, in the strange geometry of spacetime, that the true mystery of the universe begins to unfold. For most of human history, time seemed like the most reliable thing in existence. Day followed night. Seasons followed each other in quiet cycles. The stars moved across the sky with predictable precision. If you built a clock carefully enough, it would tick forward in steady, identical moments, each second passing just like the one before it. Time appeared universal. A single invisible river flowing through the entire universe, carrying everything with it. Whether you were on Earth, on the moon, or drifting somewhere far among the stars, it seemed obvious that time must pass in exactly the same way. A second was a second. An hour was an hour. The universe, it seemed, shared one common clock. But in the early 20th century, a young physicist named Albert Einstein began to suspect something unusual. He was not studying distant galaxies or powerful telescopes. Instead, he was thinking about something much simpler: light. At the time, scientists had discovered that light travels at an extremely precise speed. No matter how you measure it, light in a vacuum always moves at about 300,000 kilometers per second. That speed never changes. Not if the source of the light moves. Not if the observer moves. Not even if both are racing toward or away from each other at incredible velocities. This was deeply strange. Because in everyday life, speeds usually add together. If you throw a ball from a moving train, the speed of the ball combines with the speed of the train. Someone standing beside the tracks would see the ball traveling faster than someone sitting inside the train. But light refuses to behave this way. No matter how fast you move, the light beam beside you always appears to travel at the same speed. Einstein realized that if this strange property of light was truly fundamental, then something else in our understanding of reality had to give way. And the thing that changed was time itself. In 1905, Einstein published a theory called special relativity. One of its most surprising conclusions was that time is not absolute. Instead, time depends on motion. Imagine two identical clocks. One remains on Earth, quietly ticking away on a table. The other is placed inside a spacecraft traveling at an extremely high speed through space. According to relativity, the clock on the spacecraft will tick more slowly than the clock on Earth. This effect is known as time dilation. To the astronaut inside the spacecraft, everything would feel perfectly normal. Their heartbeat, their thoughts, even the ticking of their onboard clock would seem unchanged. But when they eventually return to Earth, they would discover that less time has passed for them than for the people who remained behind. In other words, motion can stretch time. At ordinary speeds, this effect is incredibly small. Even the fastest airplanes move far too slowly for the difference to be noticeable. But as speeds approach the speed of light, time dilation becomes dramatic. At 90% of the speed of light, time passes more than twice as slowly for the traveler compared to someone at rest. At 99% of the speed of light, the difference becomes even more extreme. And if it were possible to travel exactly at the speed of light, which no object with mass can do, time itself would appear to stop entirely. But Einstein's discoveries did not end there. 10 years later, he developed an even deeper theory known as general relativity. And this theory revealed something even stranger. Motion is not the only thing that can change the flow of time. Gravity can change it too. To understand why, Einstein proposed a radical new idea. Gravity is not simply a force pulling objects together. Instead, gravity is the result of how mass bends the structure of spacetime itself. The universe is not made of separate ingredients called space and time. They are woven together into a single fabric. Spacetime. Massive objects, planets, stars, galaxies, distort this fabric. They create curves and dips in the geometry of spacetime. And other objects move along those curves. This is what we experience as gravity. An easy way to imagine this is to picture a stretched rubber sheet. If you place a heavy ball in the center of the sheet, it creates a depression. Smaller balls placed nearby will roll toward the heavier one, not because they are pulled by an invisible force, but because the surface beneath them has curved. The real universe behaves in a similar way. Except instead of a rubber sheet, we are dealing with the geometry of spacetime itself. And when spacetime bends, something remarkable happens. Time changes its speed. Near massive objects, time flows more slowly. The stronger the gravity, the slower time passes. This effect is called gravitational time dilation. It is subtle near Earth, but it is real. Clocks placed at higher altitudes tick slightly faster than clocks at sea level. The difference is tiny, only fractions of a second over many years, but it has been measured with extremely precise atomic clocks. In fact, this effect is so important that modern technology must account for it. The satellites that make up the Global Positioning System, or GPS, orbit about 20,000 kilometers above Earth. Because they are farther from Earth's gravity, time moves slightly faster for them compared to clocks on the ground. If this difference were ignored, GPS measurements would accumulate errors of several kilometers each day. So every time you open a map on your phone and check your location, the system quietly corrects for the way gravity bends time. A small but constant reminder that time is not universal. Even here, on our familiar planet. But if gravity can slow time near Earth, imagine what happens near something far more massive. A neutron star. Or a black hole. Objects so dense that the structure of spacetime itself begins to warp dramatically. In those extreme regions, time does not merely slow by fractions of a second. It can stretch, distort, and nearly stop. And it is there, near the most powerful gravitational fields in the universe, that the ordinary flow of past, present, and future begins to behave in ways that challenge our deepest intuitions. In the next part of our journey, we will move closer to those extraordinary places. Places where gravity becomes so intense that time itself begins to bend. Places where the difference between before and after may no longer be as simple as we once believed. And as we approach those cosmic extremes, we begin to see the universe in a completely new way. Not as a place where time quietly flows forward, but as a landscape where time itself can stretch, twist, and sometimes nearly disappear. To begin understanding how gravity stretches time, it helps to imagine a simple situation. Suppose you are standing at the base of a tall mountain. Above you, perhaps several kilometers higher, someone else is standing near the summit. The two of you are separated only by altitude. The same sky stretches above you both, the same earth rests beneath your feet. At first glance, nothing about this situation seems extraordinary. And yet, according to Einstein's theory of general relativity, time is not passing in exactly the same way for both of you. The difference is incredibly small. So small that your senses could never detect it. Even ordinary clocks would not notice. But extremely precise atomic clocks can. The clock on the mountain summit ticks ever so slightly faster than the clock at the base. The reason lies in gravity. Down here, closer to the center of the Earth, gravity is slightly stronger. And stronger gravity slows the passage of time. Higher up the mountain, gravity weakens just a little, allowing time to move slightly faster. This difference is tiny, but it is measurable. In fact, physicists have tested this effect in laboratories using atomic clocks placed just centimeters apart. Even that small difference in height produces a detectable change in how time flows. It is a subtle reminder that time is not something rigid or universal. Instead, time behaves more like a flexible dimension woven into the structure of the universe. And gravity gently reshapes it. If you could observe the world with extreme sensitivity, you would notice that every object slightly alters the passage of time around it. The Earth does this. The Sun does this even more strongly. And massive stars distort time far more dramatically. But there are objects in the universe where gravity becomes so intense that these effects grow far beyond anything we experience on Earth. To understand this, we must travel far beyond our planet. Far beyond the quiet orbit of the Moon. Out past the outer planets and the distant halo of icy objects surrounding our solar system. Eventually we leave the Sun behind entirely and enter the vast star-filled disk of the Milky Way galaxy. Our galaxy contains hundreds of billions of stars, many of them far more massive than our own Sun. Most of these stars live calm and stable lives, shining steadily for millions or billions of years. But some of them end their lives in extraordinary ways. When a massive star reaches the end of its life, the balance between gravity and nuclear energy inside the star begins to collapse. For millions of years, nuclear reactions in the star's core have pushed outward, resisting the inward pull of gravity. But once the star runs out of fuel, that outward pressure fades. Gravity takes over. And the collapse begins. In a matter of seconds, the entire star can implode inward, compressing its core to astonishing densities. Sometimes this collapse produces one of the most powerful explosions in the universe. A supernova, briefly outshining entire galaxies. But the object left behind is even more fascinating. In many cases, the collapsed core becomes a neutron star. A neutron star is one of the strangest objects known to exist. Imagine compressing a mass greater than the Sun into a sphere only about 20 kilometers across. The result is an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. Gravity near the surface of a neutron star becomes extraordinarily powerful. And with that gravity comes an extreme distortion of time. If you were able to place two clocks near such a star, one far away and one close to the surface, the difference between them would become noticeable very quickly. The clock near the neutron star would tick much more slowly. From the perspective of a distant observer, time near the star would appear stretched. A minute near the surface might correspond to many minutes far away. An hour might correspond to several hours. The deeper you descend into the gravitational field, the slower time flows. This effect grows stronger and stronger as gravity intensifies. And neutron stars are only the beginning. Because there exists an even more extreme possibility. An object where gravity becomes so powerful that the distortion of spacetime reaches its ultimate limit. An object where time slows not just dramatically, but almost completely. These objects are known as black holes. Black holes form when gravity compresses matter so intensely that spacetime curves inward beyond a critical threshold. At the boundary surrounding a black hole lies a region known as the event horizon. Crossing this boundary marks a point of no return. Not because of some invisible barrier, but because spacetime itself bends inward so steeply that all possible paths lead deeper into the black hole. Even light cannot escape. But something even more extraordinary happens near this boundary. From the perspective of a distant observer watching someone approach a black hole, the traveler appears to slow down. At first the effect is subtle. But as the traveler draws closer to the event horizon, their motion seems to slow more and more. Their clock ticks more slowly. Their movements stretch out. Their signals take longer and longer to reach the outside universe. Eventually, something remarkable occurs. To the distant observer, the traveler never quite reaches the event horizon. Instead, they appear to freeze in time, hovering just above the boundary. Their image grows dimmer and redder as the light they emit becomes stretched by the extreme gravity. Over time, the signals fade away entirely. From the outside perspective, the traveler seems to pause forever at the edge of the black hole. Time, it seems, has almost stopped. Yet from the traveler's own perspective, the experience would be completely different. They would continue falling inward normally, unaware that the outside universe perceives their time as slowing. This strange difference in perception reveals something profound about the nature of time. Time is not universal. It does not flow at the same rate everywhere. Instead, time is deeply connected to the geometry of spacetime itself. Where gravity becomes extreme, time stretches. And as we move closer to the most powerful gravitational environments in the cosmos, the familiar sequence of events, before, then after, begins to behave in ways that challenge our everyday understanding. In the next part of our journey, we will move even closer to those mysterious boundaries, closer to the edge of black holes themselves. Because there, in the strange geometry surrounding these cosmic giants, the concept of time begins to blur in ways that are both unsettling and beautiful. Places where the future may become unavoidable, and where the very meaning of before and after begins to dissolve. The strange behavior of time near black holes may sound almost like science fiction. And yet, the physics behind it emerges directly from the equations of general relativity. According to Einstein's theory, spacetime is not a rigid framework. It behaves more like a flexible landscape that can bend and stretch under the influence of mass and energy. Near ordinary objects like planets or stars, the bending is gentle. But as gravity becomes stronger, the distortion becomes more dramatic. Black holes represent the most extreme example of this curvature. They form when so much mass is compressed into such a small region that spacetime itself collapses inward. The result is not simply a very dense object. It is a region where the geometry of spacetime changes so profoundly that the normal paths through space and time begin to rearrange themselves. To understand what this means, imagine standing far away from a black hole, observing a spacecraft slowly approaching it. From your distant vantage point, the spacecraft appears to fall inward toward the event horizon, the invisible boundary surrounding the black hole. At first, the motion looks ordinary. The spacecraft drifts closer. Its engines glow faintly as it adjusts its trajectory. Radio signals continue to arrive from the crew, reporting their descent. But as the spacecraft approaches the event horizon, something subtle begins to change. The signals arrive slightly more slowly. The clock inside the spacecraft appears to tick more slowly as well. At first, the difference is barely noticeable. But as the spacecraft descends deeper into the gravitational well, the effect becomes more pronounced. The light emitted from the spacecraft stretches toward longer wavelengths. Its color slowly shifts toward red. This effect is called gravitational redshift, and it happens because the immense gravity near the black hole stretches the waves of light as they climb out of the curved spacetime surrounding it. Meanwhile, the flow of time for the spacecraft continues to slow relative to the outside universe. Seconds aboard the spacecraft correspond to longer intervals for the distant observer. Minutes stretch into hours. Hours stretch into days. From the perspective of the distant observer, the spacecraft seems to move more and more slowly, as if it were drifting through thick cosmic syrup. Eventually, the motion becomes almost imperceptible. The spacecraft appears suspended just above the event horizon. Frozen. Its last signals arriving more slowly, each pulse separated by longer intervals. The light from the ship grows dimmer and redder as it struggles against the intense gravity. Then, gradually, the signals fade away entirely. To the distant observer, it appears as though the spacecraft never quite crosses the event horizon. Instead, it simply lingers there forever, its image slowly dissolving into darkness. But this is only one side of the story. Because the crew aboard the spacecraft would experience something very different. From their perspective, time continues normally. Their clocks tick as usual. Their conversations continue. Their descent toward the black hole feels smooth and uninterrupted. They would not perceive themselves slowing down or freezing in place. Instead, they would cross the event horizon without noticing any dramatic boundary. No sudden wall. No violent barrier. The event horizon is not a solid surface. It is simply a region of spacetime where the geometry becomes so extreme that all paths lead inward. Once crossed, escape becomes impossible. Not because of a physical force pulling you back, but because every possible direction in spacetime leads deeper toward the center. Inside this region, the structure of spacetime changes in a remarkable way. In the ordinary universe, we can move freely through space. Forward, backward, left, right, up, or down. But we cannot move freely through time. Time carries us relentlessly forward. Inside a black hole, these roles begin to reverse. The direction leading toward the center of the black hole becomes as unavoidable as the future itself. Just as we cannot choose to move backward in time, an object inside the event horizon cannot choose to avoid the singularity at the center. The geometry of spacetime guides every possible path toward it. In this sense, falling toward the center of a black hole becomes similar to moving forward in time. It is not something that can be avoided. It is simply where the structure of spacetime leads. For an outside observer, this entire journey appears strangely distorted. The traveler seems frozen near the event horizon, their time stretched almost to a halt. But within the traveler's own experience, the journey continues normally. This dual perspective is one of the most fascinating consequences of relativity. It reminds us that time is not a universal backdrop shared by all observers. Instead, time depends on where you are and how you move through spacetime. Near massive objects, time bends. Near neutron stars, it stretches. And near black holes, it approaches a strange limit where the flow of time for distant observers appears to nearly stop. But black holes are only one example of how the universe can distort our familiar understanding of time. Because if gravity can stretch time in such dramatic ways, then perhaps there are places in the universe where time behaves even more strangely. Places where the distinction between past and future becomes blurred. Places where the sequence of events we rely on, cause followed by effect, begins to lose its usual meaning. To explore those places, we must move even deeper into the strange geometry of spacetime. And the closer we look, the more we begin to realize that time itself may not be the simple, steady river we once imagined. Instead, time may be something far more subtle. A dimension that bends and stretches across the universe. A dimension that, in certain regions of the cosmos, may even begin to break. If gravity can stretch time, then black holes are where this effect reaches its most dramatic expression. They are among the strangest objects in the universe. Invisible, silent, and yet capable of bending space and time to an extraordinary degree. A black hole does not shine like a star. It does not glow with nuclear fire. In fact, a black hole emits no light at all. What we see instead is the influence it has on the world around it. Gas spiraling inward. Stars orbiting an invisible center. Light from distant galaxies bending as it passes nearby. These subtle clues reveal the presence of something immensely powerful, hidden within the darkness. At the heart of a black hole lies an object so dense that the curvature of spacetime becomes extreme. But the most fascinating region is not the center. It is the boundary surrounding it. A boundary known as the event horizon. The event horizon is not a physical surface. There is no wall or shell marking its location. Instead, it is a threshold within spacetime itself. A place where the geometry of the universe changes in a profound way. Outside this boundary, escape is still possible. A beam of light can still travel outward. A spacecraft can still fire its engines and move away. But once something crosses the event horizon, all possible paths through spacetime lead inward. Even light can no longer climb back out. This is why black holes appear completely dark. Their gravity is not simply strong. It reshapes spacetime so severely that the paths light normally follows become trapped. But the event horizon is also where time behaves in its most mysterious way. Imagine once again that distant observer watching a spacecraft approach a black hole. The spacecraft begins far away, where gravity behaves almost normally. Its engines glow softly as it drifts toward the dark center. From the observer's perspective, the ship moves steadily closer. But as the spacecraft approaches the event horizon, something subtle begins to happen. The signals from the ship arrive more slowly. Its onboard clock appears to tick more slowly as well. This is gravitational time dilation becoming stronger. The closer the spacecraft moves toward the black hole, the deeper it falls into the curved geometry of spacetime. And the deeper it falls, the slower time appears to move. From the astronaut's perspective inside the spacecraft, nothing unusual happens. Their watch ticks normally. Their breathing remains steady. If they glance out the window, the distant stars still shine in the darkness. But to the distant observer, everything aboard the spacecraft begins to slow. The ship's movements stretch out. Its signals arrive with increasing delay. The light leaving the spacecraft grows redder and dimmer as gravity stretches its wavelength. This phenomenon, gravitational redshift, becomes more intense the closer the ship moves toward the event horizon. Eventually, the ship appears to slow almost to a halt. Its descent becomes nearly frozen in time. From the observer's perspective, the spacecraft seems suspended just above the event horizon, hovering there indefinitely. The signals arriving from the ship become weaker. The intervals between them grow longer. 1 minute between transmissions. Then an hour. Then a day. Eventually, the signals fade completely. The spacecraft appears to vanish, its image dissolving into darkness. To the outside universe, it seems as though the ship never quite crosses the event horizon at all. Instead, it remains forever trapped at the boundary, frozen in time. But the astronauts inside the spacecraft would experience something entirely different. To them, the descent continues normally. Their clocks tick. Their conversations continue. And when they finally cross the event horizon, they would notice nothing special at all. There would be no sudden flash. No dramatic barrier. No physical surface marking the crossing. The event horizon is not something you can touch. It is simply the point where the geometry of spacetime changes so completely that escape becomes impossible. Once inside, every path forward leads deeper into the black hole. This difference between perspectives reveals something extraordinary about the nature of time. Time is not a universal experience shared equally by all observers. Instead, time depends on where you are in spacetime. Two observers watching the same event can experience time in entirely different ways. For the distant observer, the spacecraft seems to freeze at the event horizon. For the astronauts inside, the journey continues normally. Both perspectives are correct within the strange geometry of relativity. And it is this strange duality that makes black holes one of the most fascinating laboratories in the universe. Because near the event horizon, the familiar relationship between past, present, and future begins to behave in unusual ways. The deeper we explore this boundary, the more we begin to see that time itself is not as simple as it appears. Instead of a steady river flowing forward through the universe, time begins to behave more like a landscape. A landscape that bends under the influence of gravity. A landscape where different observers can follow different paths. And at the edge of a black hole, that landscape becomes so distorted that the difference between before and after begins to blur. In the next part of our journey, we will move even closer to this mysterious boundary. Closer to the event horizon itself. Because there, in the strange curvature of spacetime, we begin to encounter one of the most remarkable ideas in modern physics. The idea that time itself may behave differently depending on how you look at it. And that near a black hole, the universe begins to reveal just how flexible the fabric of spacetime truly is. To understand just how unusual the edge of a black hole really is, it helps to slow down and imagine the journey step by step. Suppose a spacecraft approaches a black hole very carefully, moving slowly enough to observe what happens along the way. Far from the black hole, space behaves almost normally. Stars shine in the distance, and time flows much as it does here on Earth. But as the spacecraft drifts closer, gravity begins to tighten its grip. The stars behind the black hole appear distorted. Their light bends as it passes through the warped spacetime surrounding the massive object. This bending of light creates strange visual effects. Sometimes distant stars appear stretched into thin arcs of light, forming shapes that seem almost like glowing rings around the darkness. Astronomers call these distortions gravitational lensing. It happens because spacetime near a black hole curves so strongly that even the paths of light are redirected. But the deeper the spacecraft travels into this curved region, the more dramatic the effects become. Light from the outside universe begins to behave strangely. Signals arriving from distant stars speed up. From the perspective of someone falling toward the black hole, the outside universe would appear to evolve faster and faster. Events that might normally take years or centuries begin to unfold more quickly. If the astronaut could look far enough into space, they might even glimpse distant galaxies changing over enormous spans of time. Meanwhile, to observers far away from the black hole, the opposite effect occurs. They watch the astronaut slow down. From their perspective, the spacecraft moves through time more and more slowly as it approaches the event horizon. This strange difference arises because gravity reshapes the structure of spacetime. The deeper an object falls into the gravitational well of the black hole, the more the flow of time shifts relative to distant observers. And near the event horizon, this distortion becomes extreme. Imagine placing a clock just outside the event horizon. Now imagine another clock far away from the black hole, drifting safely in deep space. To the distant observer, the clock near the event horizon appears to tick more slowly. Tick. Pause. Tick. Pause. Each second stretching longer and longer. The closer the clock moves toward the event horizon, the more dramatic this stretching becomes. Eventually, from the distant observer's perspective, the ticking almost stops entirely. Time near the horizon seems frozen. Yet this is not because the clock has stopped. Instead, it is because the geometry of spacetime near the black hole has become so distorted that signals from that region take longer and longer to reach the outside universe. Light climbing away from the intense gravity loses energy as it escapes. Its wavelength stretches. Its color shifts toward red. This effect continues until the light becomes so stretched that it fades beyond detection. From the outside, the object appears to disappear. But the object itself has not vanished. It has simply crossed into a region where the paths of light and time behave differently. This is one of the reasons black holes seem so mysterious. They hide their interior from the rest of the universe. Once something passes the event horizon, no information can return. Not even light. And yet the event horizon itself is not a sharp physical surface. If an astronaut were falling freely toward it, they would not feel a sudden jolt or collision. Instead, they would drift across the boundary smoothly, almost unnoticed. For a sufficiently large black hole, the tidal forces at the event horizon might even be gentle enough that a traveler could cross without immediate danger. But deeper inside, the situation becomes far more extreme. Gravity grows stronger and stronger. The curvature of spacetime increases dramatically. Eventually, the traveler would encounter forces so powerful that no known material could survive. But long before reaching that final fate, something profound has already happened. The relationship between time and space has begun to change. Outside the black hole, time flows forward while space offers many directions of movement. We can walk north or south. We can travel east or west. But we cannot choose to move backward through time. Time carries us forward whether we wish it or not. Inside the event horizon, the structure of spacetime rearranges these possibilities. The direction leading toward the center of the black hole becomes as inevitable as the future. Just as we cannot avoid moving forward in time, an object inside the horizon cannot avoid moving toward the singularity. Every possible path leads inward. In this strange region, falling toward the center becomes something like moving forward through time. It is no longer simply a direction in space. It becomes a destination built into the structure of spacetime itself. And this is where the familiar ideas of past and future begin to grow uncertain. Because if gravity can distort time so dramatically near black holes, then time may not be a simple universal river flowing through the cosmos. Instead, it may be something far more flexible. Something shaped by the geometry of spacetime. Something that bends and stretches depending on where you are in the universe. Black holes show us that the universe allows time to behave in ways that seem almost impossible from our everyday perspective. And yet these behaviors emerge naturally from the laws of physics that describe gravity itself. But black holes are not the only places where our understanding of time begins to falter. There is another moment in the history of the universe where the concept of time itself becomes uncertain. A moment when the entire cosmos was compressed into an unimaginably dense state. A moment when space itself may not yet have fully existed. To explore that moment, we must travel not across space, but backward through the history of the universe. Back toward the earliest instant of cosmic time. Back toward the beginning of everything we know. The moment we call the Big Bang. For many years, black holes were thought of as little more than mathematical curiosities. They appeared in the equations of general relativity as strange solutions. Regions where gravity became infinitely strong and spacetime curved inward without limit. At first, even Einstein himself suspected that such objects might never truly exist in nature. The idea seemed too extreme. A place where light could not escape. A region where time slowed almost to a halt. But over the decades, astronomers began to find evidence that black holes were not just theoretical ideas. They were real. And they were everywhere. At the centers of many galaxies, including our own Milky Way, astronomers discovered something remarkable. Stars near the galactic center were orbiting around an invisible object. They moved at incredible speeds, completing orbits in just a few years. The gravitational pull required to hold them in such tight orbits could only come from something immensely massive. Yet nothing visible was there. No glowing star. No cluster of ordinary matter. Only darkness. Today we know that at the center of the Milky Way lies a supermassive black hole known as Sagittarius A. It contains a mass about 4 million times greater than the Sun. And our galaxy is not unique. Observations suggest that nearly every large galaxy in the universe contains a supermassive black hole at its center. Some of them are billions of times more massive than our Sun. These enormous objects shape the evolution of entire galaxies. They influence the motion of stars, the flow of gas, and even the formation of new stars across cosmic time. And yet, despite their enormous influence, the true nature of what lies beyond the event horizon remains hidden. Because once information crosses that boundary, it cannot return. The interior of a black hole is forever concealed from the outside universe. This makes black holes one of the greatest mysteries in modern physics. We can observe how matter behaves around them. We can measure their mass and their spin. We can even capture images of the glowing gas swirling around their event horizons, as astronomers did in 2019 with the Event Horizon Telescope, revealing the first direct image of a black hole's shadow. But what happens inside remains unknown. According to general relativity, everything that falls into a black hole eventually approaches the singularity at its center. The singularity is a point where density becomes infinite and the curvature of spacetime becomes extreme. At that point, the equations of general relativity break down. They can no longer describe what happens. This suggests that our current understanding of physics is incomplete. Some deeper theory, perhaps a future theory of quantum gravity, may eventually explain what truly happens inside black holes. But even without fully understanding the interior, black holes have already taught us something profound. They reveal that time is not an independent backdrop for the universe. Time is part of the fabric of spacetime itself. And that fabric can bend, stretch, and even trap light and information within certain regions. Near the event horizon, the stretching of time becomes so extreme that two observers can experience the same event in radically different ways. One observer may see an object frozen in time. Another may experience the same journey unfolding normally. Both perspectives are valid. Both arise naturally from the geometry of spacetime. This realization forces us to rethink the simple idea that time flows uniformly everywhere. Instead, time becomes something more dynamic. Something shaped by gravity. Something that depends on where you are and how you move through the universe. And once we accept that time can bend and stretch in this way, another question begins to emerge. If gravity can distort time near black holes, could time itself have a beginning? Because black holes represent one kind of extreme environment. But there is another moment in the history of the universe where spacetime itself reached extraordinary conditions. A moment when the entire observable universe was compressed into a state far denser than any black hole. A moment when the familiar structure of space and time may not yet have fully existed. To find that moment, we must travel back through cosmic history. Past the formation of galaxies. Past the birth of the first stars. Past the cooling of the early universe. Back to a time when the universe itself was only a fraction of a second old. A time when temperatures were so high that atoms could not exist. A time when matter and energy blended together in a seething ocean of particles. As we approach that early moment, the equations of physics begin to behave strangely. The familiar concepts of space and time begin to blur. And eventually we reach a boundary where our current understanding of physics can no longer fully describe what happened. This boundary marks the earliest moment we can meaningfully describe. The moment known as the Big Bang. And it raises one of the most profound questions in all of science. If time can stretch near black holes. If gravity can bend the flow of time itself. Then what happened at the very beginning of the universe? Was there a moment before the Big Bang? Or was the Big Bang not simply the beginning of the universe, but the beginning of time itself? To explore that mystery, we must leave the edges of black holes behind and turn our attention to the earliest chapter of cosmic history. A chapter where the familiar sequence of before and after may not yet have existed at all. And where the true nature of time begins to reveal itself in ways both subtle and profound. When we look into the night sky, we are not only looking across space. We are also looking back through time. Light travels extremely fast, but it does not move instantly. Even the light from our own sun takes about 8 minutes to reach Earth. When you see sunlight on your skin, you are actually seeing the sun as it was 8 minutes ago. The same principle applies across the universe. The nearest stars appear to us as they were years ago. More distant stars appear as they were hundreds or thousands of years in the past. When we observe distant galaxies, we see them as they existed millions or even billions of years ago. Astronomy, in this sense, is a form of time travel. The deeper our telescopes peer into the cosmos, the further back into the history of the universe we are able to see. And over the past century, astronomers have pushed this window further and further. Powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope have allowed us to observe galaxies whose light has traveled for more than 13 billion years before reaching Earth. These ancient galaxies appear small and faint, but they carry with them a remarkable story. They show us what the universe looked like when it was still very young. When astronomers examine these distant galaxies, they notice something curious. Nearly all of them are moving away from us. Not because our galaxy occupies some special central position in the universe, but because the entire fabric of space is expanding. Every distant galaxy appears to be receding from every other galaxy. This discovery transformed our understanding of the cosmos. Before the 20th century, many scientists believed that the universe was eternal and unchanging. But if the universe is expanding today, then in the past it must have been smaller. And if we continue tracing this expansion backward through time, we eventually reach a moment when everything in the observable universe was compressed into an extremely dense state. This early moment is what we call the Big Bang. Despite its name, the Big Bang was not an explosion in space. It was an expansion of space itself. At the earliest moments of cosmic history, the universe was unimaginably hot and dense. Matter and energy were packed together so tightly that the familiar structures we know today, atoms, stars, galaxies, could not yet exist. Instead, the universe was filled with an intense sea of particles and radiation. Temperatures were so high that even the building blocks of atoms could not remain stable. Protons and electrons existed freely, colliding constantly within a glowing plasma that filled all of space. As the universe expanded, it gradually cooled. After about 380,000 years, temperatures dropped enough for electrons and protons to combine into the first atoms. When this happened, light was finally able to travel freely through space without constantly scattering off charged particles. That ancient light still fills the universe today. It is known as the cosmic microwave background. Sensitive instruments can detect this faint radiation in every direction of the sky. It is the oldest light we can observe, a quiet echo from the early universe, still traveling through space after more than 13 billion years. This discovery provided powerful evidence that the universe truly did begin in a hot, dense state. But as physicists explored the earliest moments of the Big Bang, they encountered something deeply puzzling. When we trace the expansion of the universe backward toward the beginning, the density of matter and energy increases dramatically. Temperatures climb higher and higher. The curvature of spacetime becomes more extreme. Eventually we approach a point where the equations describing the universe begin to break down. According to classical general relativity, the universe would shrink toward a singularity, a state of infinite density and temperature. At this point, the known laws of physics can no longer describe what happens. The mathematics simply stops working. This situation is strangely similar to what happens at the center of a black hole. In both cases, the equations of general relativity predict a singularity where spacetime becomes infinitely curved. But physicists suspect that these infinities are not physical realities. Instead, they signal that our current theories are incomplete. Just as the interior of black holes likely requires a deeper theory of physics, the earliest moments of the universe may require a new understanding of spacetime itself. Yet even without fully solving this mystery, the Big Bang reveals something profound about the nature of time. Because when we trace the history of the universe backward toward that initial moment, something unusual happens. time itself appears to approach a boundary. In our everyday experience, time stretches endlessly into the past. We can imagine yesterday, last year, or centuries ago. But the Big Bang suggests that time may not extend infinitely backward. Instead, time itself may have begun at that early moment. If this is true, then asking what happened before the Big Bang might be similar to asking what lies north of the North Pole. The question assumes a direction that may not exist. Time may simply begin there. A starting point for the unfolding history of the universe. But this idea raises even deeper questions. If time truly began with the Big Bang, then what does it mean for time to begin? How can something like time, the dimension in which change and motion occur, suddenly come into existence? To explore that mystery, we must look more closely at the earliest fractions of a second after the universe began expanding. Moments when the familiar concepts of space, matter, and time were still taking shape. Moments when the universe was far stranger than anything we observe today. And as we move closer to that beginning, we begin to see that the nature of time itself may be far more subtle than we once imagined. When we try to imagine the beginning of the universe, our minds naturally reach for familiar images. We picture an empty space suddenly erupting with energy, a burst of light expanding outward into darkness. But this picture, while dramatic, is not quite accurate. The Big Bang did not occur inside space. It was the moment when space itself began expanding. Every region of the universe was once compressed into a state far hotter and denser than anything we see today. There was no central point from which matter exploded outward. Instead, the expansion happened everywhere at once. Every galaxy we observe today began much closer to every other galaxy. As the universe expanded, the distances between them grew. To imagine this, some cosmologists use a simple analogy. Picture a balloon with small dots drawn across its surface. Each dot represents a galaxy. As the balloon inflates, the surface stretches, and the dots move farther apart from each other. No single dot sits at the center of the expansion. From the perspective of any one dot, all the others appear to be moving away. The universe behaves in a similar way, except that the expansion occurs in 3 dimensions rather than on the surface of a balloon. But the analogy also hints at something deeper. If we imagine reversing the expansion of the balloon, shrinking it smaller and smaller, eventually all the dots would converge toward a single compressed state. Something like that appears to have happened in the early universe. As we trace the cosmic expansion backward in time, galaxies move closer together. Clusters merge. Matter compresses. Temperatures rise. Eventually we reach an era when stars had not yet formed. Then an even earlier time when atoms themselves could not exist. Earlier still, when protons and neutrons had not yet taken shape. The universe becomes a rapidly changing sea of energy and fundamental particles. And as we approach the very earliest moments, the conditions become so extreme that our current theories struggle to describe what happened. The laws of physics that govern the everyday world begin to blur together. Gravity, electromagnetism, and the nuclear forces may have behaved differently under such enormous temperatures and densities. Physicists believe that during the earliest fractions of a second, the universe passed through several extraordinary phases. In the first moments after the Big Bang, the universe may have undergone a period of incredibly rapid expansion known as cosmic inflation. During inflation, space itself expanded faster than the speed of light. This does not violate the laws of relativity because nothing was traveling through space faster than light. Instead, the space between points expanded. Within a tiny fraction of a second, the universe may have grown from something smaller than a subatomic particle to something vast enough to contain the seeds of galaxies. Inflation helps explain several puzzling features of the universe we observe today. It explains why the universe appears remarkably smooth and uniform on large scales. It explains why distant regions of the cosmos share nearly identical physical properties. And it explains why the geometry of the universe appears so close to perfectly flat. But inflation also deepens the mystery of the universe's beginning. Because if inflation occurred, it suggests that the early universe behaved in ways that challenge our intuitive understanding of time and space. Some models of inflation even suggest that the Big Bang may not have been the absolute beginning of everything. Instead, it might represent a transition from an earlier state of the cosmos. Perhaps the universe emerged from a quantum fluctuation. Perhaps it formed from the collapse of an earlier universe. Perhaps the Big Bang was simply one event in a much larger cosmic process. Physicists continue to explore these possibilities. But even within the most cautious scientific models, one idea remains deeply intriguing: the possibility that time itself began with the Big Bang. If this is true, then the familiar flow of past, present, and future did not exist before that moment. There was no earlier time waiting for the universe to appear. Instead, time itself came into existence along with space. In this view, the Big Bang is not simply the beginning of matter and energy. It is the beginning of spacetime itself. The moment when the fabric of the universe first unfolded. This concept can feel difficult to grasp because our everyday experience is built around the assumption that time always stretches endlessly into the past. We imagine earlier and earlier moments, just as we imagine traveling farther and farther across space. But if time has a beginning, then the past may have a boundary. A limit beyond which the concept of before no longer applies. In the same way that the surface of the Earth has no point north of the North Pole, the history of the universe may have no moment earlier than the Big Bang. Time itself may simply start there. This idea does not necessarily answer every question about the origin of the universe. Instead, it reveals how deeply our understanding of time is tied to the structure of spacetime itself. And it hints that the nature of time may be far more subtle than the steady ticking of clocks suggests. Because once we begin exploring the earliest moments of cosmic history, we discover something surprising. The laws of physics do not always distinguish clearly between past and future. At the deepest levels of physical theory, many equations work equally well whether time moves forward or backward. This symmetry suggests that the direction we experience, the arrow of time flowing from past to future, may not be a fundamental feature of the universe. Instead, it may arise from deeper physical processes that unfolded as the universe evolved. To understand this strange possibility, we must look more closely at the nature of time itself. And the more we explore, the more we begin to realize that time may not be the simple river we once imagined. It may be something more like a landscape. A structure woven into the fabric of spacetime. A structure that can stretch, bend, and perhaps even lose its familiar direction under the most extreme conditions in the universe. In the next part of our journey, we will explore that idea more deeply. Because at the smallest scales of physics, in the strange world of quantum mechanics, the very meaning of time begins to shift once again. When scientists speak about the beginning of the universe, they often describe it using the language of physics. Temperatures, densities, expansion rates, equations that trace the evolution of the cosmos from its earliest moments to the vast structure we observe today. But beneath those equations lies a much deeper question. Not simply how the universe began, but what it means for something like time itself to have a beginning. For most of our lives, time feels like an endless backdrop. Moments pass. Days turn into years. History stretches backward through centuries of human civilization. Even beyond that, we imagine earlier and earlier moments in the past, Ancient forests, the age of dinosaurs, the formation of the Earth, the birth of the Sun. Our minds easily extend this chain of events further into the past. Earlier stars. Earlier galaxies. Earlier cosmic epochs. But when cosmologists follow this chain far enough, they encounter a boundary. A moment when the familiar descriptions of space and time begin to dissolve. This boundary lies extremely early in the history of the universe. Roughly 13.8 billion years ago, according to our best measurements. At that moment, the observable universe existed in a state of extraordinary density and temperature. All of the matter and energy we see today was compressed into an unimaginably small region. Space itself was far smaller. And the flow of time, as we understand it, was just beginning to unfold. But what makes this moment especially mysterious is that the equations of physics begin to behave strangely as we approach it. General relativity, which describes the behavior of gravity in spacetime, works remarkably well across the universe. It explains the motion of planets, the bending of light near massive stars, the expansion of the cosmos, and even the existence of black holes. But when we push the equations of general relativity all the way back toward the earliest instant of the Big Bang, something unusual happens. The equations predict a singularity, a point where density becomes infinite, where temperature becomes infinite, where the curvature of spacetime becomes infinite. Infinities like these usually signal that a theory has reached the limits of its usefulness. They suggest that the equations we are using no longer fully describe reality. Physicists believe that near the beginning of the universe, the effects of quantum mechanics become just as important as gravity. Yet today we do not possess a complete theory that successfully combines these two frameworks. General relativity describes gravity and the large-scale structure of spacetime. Quantum mechanics describes the behavior of matter and energy at the smallest scales. Both theories work extraordinarily well in their own domains. But when we attempt to apply them together to the earliest moments of the universe, the mathematics becomes uncertain. This is why many physicists believe that a deeper theory, often called quantum gravity, will eventually provide a clearer description of what truly happened at the beginning of cosmic history. Such a theory might reveal that the Big Bang was not a singular point at all. Instead, it may have been a transition from an earlier quantum state of spacetime. In some theoretical models, spacetime itself emerges gradually from a more fundamental quantum structure. In others, the universe may undergo cycles of expansion and contraction, with the Big Bang representing the beginning of the current cycle. And in still other models, the universe may be part of a much larger cosmic landscape where many universes form and evolve. At present, these ideas remain speculative. Yet they all share one remarkable feature. They challenge the assumption that time must extend infinitely into the past. Instead, they suggest that time itself may have emerged as the universe evolved. In the earliest quantum state of the cosmos, the familiar distinction between past and future may not have existed at all. The universe may have begun in a condition where time, as we experience it, had not yet taken shape. If this idea is correct, then the Big Bang marks not simply the beginning of matter or energy. It marks the beginning of temporal order. The moment when the sequence of events, one moment following another, first began to unfold. Before that, the concept of earlier may simply not apply. Just as there is no location north of the North Pole, there may be no moment before the beginning of time. For many people, this idea can feel unsettling. It challenges the deeply rooted intuition that every event must have a cause that came before it. But the universe does not always conform to our everyday expectations. At the deepest levels of physics, the structure of reality often behaves in ways that seem unfamiliar and surprising. The origin of time may be one of those mysteries. And even more intriguing is what happens when we examine the laws of physics themselves. Because when physicists write down the fundamental equations describing the universe, they often notice something curious. Many of those equations do not actually prefer a direction for time. They work equally well whether time moves forward or backward. The equations describing the motion of particles, the interactions of forces, and even many processes in quantum mechanics remain valid if the direction of time is reversed. This symmetry raises a fascinating question. If the laws of physics do not strongly distinguish between past and future, why does time seem to flow in only one direction? Why do we remember the past but not the future? Why does a broken glass shatter into pieces, but the pieces never spontaneously leap back together? To understand this puzzle, we must explore the deeper nature of time itself. And to do that, we must venture into the strange and subtle world of quantum physics. Because at the smallest scales of the universe, the familiar flow of time begins to behave in ways that are even more mysterious than anything we encounter among stars and galaxies. And as we explore that world, we may begin to see that the arrow of time, the steady march from past to future, is not as fundamental as it first appears. For most of our daily lives, time feels simple. It moves forward. Morning becomes afternoon, afternoon becomes evening, and eventually the quiet hours of night arrive again. The sequence feels natural and predictable. Events appear to unfold in a clear order. First something happens, and then something else follows. A cause comes before its effect. This pattern feels so obvious that we rarely question it. Yet when physicists began studying the smallest building blocks of nature, they discovered that reality does not always behave in such a straightforward way. At the scale of atoms and particles, the universe becomes a far stranger place. Here, the familiar rules that guide our everyday experiences begin to blur. Particles behave like waves. Objects can exist in multiple states at once. And the clear sequence of events that we associate with time becomes less certain. This strange domain is known as quantum mechanics. Quantum mechanics is one of the most successful scientific theories ever developed. Its predictions have been confirmed with astonishing accuracy, guiding technologies from lasers to computer chips to the delicate atomic clocks that measure time with extraordinary precision. And yet, despite its success, the theory describes a universe that behaves very differently from the one we experience at human scales. One of the most unusual aspects of quantum mechanics is the way it treats time. In many classical descriptions of the world, time acts like a steady background. Objects move through space while time quietly ticks forward in the background. But in the quantum world, things are not always so simple. Particles are described not as tiny solid objects but as probability waves. These waves represent the range of possible states a particle might occupy. Only when a measurement is made does the particle appear in a definite position. Until that moment, its behavior is described by a spread of possibilities. This idea may sound strange, but it has been confirmed repeatedly in experiments. Electrons passing through tiny openings create interference patterns, behaving like waves rather than particles. Atoms can exist in superpositions, occupying multiple states simultaneously. And in carefully designed experiments, even large molecules can display quantum interference. The deeper physicists explored these behaviors, the more they realized that the quantum world does not always follow the intuitive flow of cause and effect we experience in everyday life. Instead, events sometimes appear to be connected in ways that transcend simple sequences in time. Consider one of the most famous quantum phenomena: entanglement. When two particles become entangled, their properties become linked in such a way that measuring one instantly reveals information about the other, even if the two particles are separated by enormous distances. If you measure the spin of one entangled particle, the spin of its partner becomes immediately determined as well. This effect occurs regardless of how far apart the particles are. Experiments have demonstrated entanglement across distances of many kilometers. Some proposals even suggest that entanglement could persist across astronomical distances. At first glance, this behavior seems to challenge the ordinary flow of time and space. It can appear as though information travels instantly between particles. But quantum mechanics does not actually allow faster than light communication. Instead, entanglement reveals something deeper about how the universe organizes information. The state of the entangled system must be described as a single unified whole, even when its parts are separated. And this idea hints at something remarkable. At the most fundamental level of physics, the universe may not be built from isolated objects interacting through simple sequences of events. Instead, it may be structured through relationships that exist across spacetime. Relationships that do not always respect the clear boundaries between past and future that we experience in everyday life. Physicists studying the mathematics of quantum theory have noticed something curious about the equations that describe these systems. Many of them remain valid whether time moves forward or backward. If we take the equations describing the motion of quantum particles and reverse the direction of time, the mathematics continues to work. This symmetry suggests that the fundamental laws governing particles do not strongly prefer a particular direction for time. Yet our experience clearly does. We remember the past. We anticipate the future. Broken objects remain broken. Ice cubes melt in warm water, but melted water never spontaneously gathers itself into a perfect cube of ice. Somewhere between the quantum world and the everyday world, a direction for time emerges. A direction often called the arrow of time. Understanding where this arrow comes from has become one of the most fascinating questions in modern physics. Because if the underlying laws of nature are largely symmetric with respect to time, then the flow of time we experience may not be a fundamental feature of reality. Instead, it may arise from deeper statistical processes shaping the evolution of the universe. Processes that began in the earliest moments after the Big Bang. Processes that gradually gave time its familiar direction. To understand those processes, we must look more closely at how order and disorder evolve across the universe. And that leads us to one of the most important ideas in all of physics. An idea known as entropy. Entropy describes how systems naturally evolve toward states of greater disorder. It is the reason heat spreads through a room. The reason stars eventually exhaust their fuel. And the reason the arrow of time points steadily from past to future. In the next part of our journey, we will explore how entropy shapes the flow of time itself. And how the quiet increase of disorder across the universe may explain why the future always feels different from the past. If the fundamental laws of physics do not strongly prefer a direction for time, then something else must explain why time seems to flow so clearly from past to future. We remember yesterday, but we cannot remember tomorrow. We can influence what happens next, but we cannot change what has already occurred. The difference between past and future feels deeply embedded in our experience of reality. Yet the equations that describe the motion of particles, the interactions of forces, and even many processes in quantum physics often look almost identical whether time moves forward or backward. This puzzle led physicists to search for something that could explain the arrow of time. The reason time appears to move in a single direction. And the answer, at least in part, lies in a concept known as entropy. Entropy is a measure of disorder. More precisely, it describes the number of possible ways a system can arrange its components while still appearing roughly the same at a larger scale. To understand this idea, imagine a simple example. Picture a brand new deck of cards. When the deck is freshly opened, the cards are arranged in a very particular order. Hearts together. Clubs together. Diamonds and spades neatly grouped. This arrangement is highly ordered. Now imagine shuffling the deck thoroughly. The cards mix together in countless possible ways. Each shuffle creates a new arrangement. But almost all of those arrangements appear disordered. The original neat sequence is extremely unlikely to appear again by chance. This illustrates an important feature of entropy. There are far more ways for a system to be disordered than ordered. Because of this, systems naturally evolve toward states of greater disorder. Not because the universe actively prefers chaos, but simply because disordered states are vastly more numerous. This statistical tendency shapes many familiar processes. When you place an ice cube into a glass of warm water, the ice melts. The cold and warm regions gradually mix until the entire glass reaches a uniform temperature. Heat spreads outward. Energy disperses. The system becomes more disordered. The reverse process, warm water spontaneously separating into hot and cold regions while forming a perfect cube of ice, is not impossible according to the fundamental laws of physics. But it is so extraordinarily unlikely that we never observe it. This tendency for entropy to increase is summarized by one of the most important principles in physics: the second law of thermodynamics. The second law states that in an isolated system, entropy tends to increase over time. Disorder grows. Energy spreads. Structure gradually dissolves. And this steady increase in entropy provides a natural direction for time. The past is the state with lower entropy. The future is the state with higher entropy. In other words, the arrow of time may emerge not from the basic laws of motion themselves, but from the statistical evolution of large systems. And the entire universe appears to follow this principle. Over billions of years, stars burn their fuel and radiate energy into space. Galaxies evolve. Structures form and eventually dissipate. Energy spreads outward through the cosmos. Entropy steadily increases. But this idea leads to another fascinating question. If entropy tends to increase over time, then the early universe must have begun in an extremely low entropy state. Otherwise, there would be no direction for entropy to increase. This is one of the deepest mysteries in cosmology. The early universe, shortly after the Big Bang, was remarkably smooth and uniform. Matter and energy were distributed almost perfectly evenly across space. At first glance, this might seem like a disordered condition. But in terms of gravity and cosmic structure, it represents an extraordinarily low entropy state. Over time, gravity amplified tiny fluctuations in density. Regions with slightly more matter began attracting more material. Clouds of gas collapsed into stars. Stars gathered into galaxies. Galaxies formed clusters connected by enormous filaments across the cosmic web. These structures represent a gradual increase in cosmic complexity. And with that complexity comes a steady rise in entropy. The universe evolves toward states that allow more possible configurations of matter and energy. But why did the universe begin in such an unusually ordered condition? Why did the Big Bang start with such low entropy? This question remains one of the greatest unsolved problems in physics. Some scientists believe the answer may lie in the nature of cosmic inflation. Others suggest that the structure of spacetime itself may favor certain initial conditions. Still others explore the possibility that our universe emerged from a larger cosmic system where low entropy beginnings occasionally occur. For now, the origin of the arrow of time remains an open mystery. But what we do know is that the steady increase of entropy gives our universe a sense of direction. It separates past from future. It allows memories to accumulate. It allows stars to shine and eventually fade. It gives time the familiar flow that shapes our lives. And yet, when we look closely at the smallest scales of the quantum world, this direction begins to blur once again. Particles do not always follow simple sequences of cause and effect. Events can interfere with each other across time. Some interpretations of quantum theory even allow processes that appear to move both forward and backward through time simultaneously. These strange possibilities suggest that the arrow of time we experience may be a large-scale feature emerging from deeper laws that are far more symmetrical. And as physicists continue exploring the relationship between quantum mechanics, gravity, and cosmology, they are beginning to uncover hints that time itself may not be a fundamental ingredient of the universe. Instead, time may be something that emerges from deeper physical processes. Processes that shape the geometry of spacetime. Processes that connect events across the cosmos in ways we are only beginning to understand. In the next part of our journey, we will explore one of the most intriguing ideas to emerge from modern physics. The possibility that the entire universe, past, present, and future, may exist together as a single structure within spacetime. A concept sometimes called the block universe. An idea that challenges the very notion that time flows at all. When we step back and look at the universe as a whole, the arrow of time appears unmistakable. Stars are born, shine for millions or billions of years, and eventually fade. Galaxies collide and merge. Planets cool and change over immense spans of time. And within those vast cosmic processes, smaller stories unfold. Seasons change. Mountains slowly erode. Living creatures grow older. Everything seems to move steadily from past toward future. Yet the deeper physicists investigate the laws governing the universe, the more they discover that this forward flow of time may not be as fundamental as it appears. At the level of basic physical laws, the universe often behaves with remarkable symmetry. If we were to record the motion of two billiard balls colliding on a perfectly smooth table, the equations describing their motion would work just as well if the film were played backward. The balls would still obey the same laws of motion. Nothing in those equations demands that time must move in only one direction. This kind of symmetry appears again and again in physics. Many of the mathematical rules describing particles and forces remain valid if time is reversed. In principle, the universe could evolve forward or backward through time while still obeying the same fundamental laws. Yet in our experience, the difference between past and future feels obvious. We remember the past. We do not remember the future. Eggs fall and shatter, but shattered eggs do not spontaneously reassemble themselves. Smoke spreads through the air but never gathers itself neatly back into a cigarette. These familiar processes reflect the steady growth of entropy. Disorder increases. Energy spreads. And this statistical tendency gives time its apparent direction. But this explanation raises an even deeper question. Why did the universe begin in such an incredibly low entropy state? For entropy to increase, there must have been a starting point where order was unusually high. And that starting point appears to have been the early universe itself. Shortly after the Big Bang, matter and energy were distributed across space with extraordinary uniformity. Tiny fluctuations existed, but overall the cosmos was remarkably smooth. This state allowed gravity to slowly amplify those fluctuations, eventually forming the stars, galaxies, and cosmic structures we observe today. But why the universe began in this special condition remains unknown. Some physicists believe that the answer may lie in the nature of spacetime itself. Others suspect that deeper quantum laws governing the birth of the universe may naturally produce such low entropy beginnings. And some theories suggest that our universe may be only one of many, each with different initial conditions. For now, the question remains open. Yet the connection between entropy and time reveals something important. The arrow of time may not be a fundamental property of the universe. Instead, it may be a statistical feature emerging from the way large systems evolve. At the microscopic level, the laws of physics remain mostly indifferent to the direction of time. But when enormous numbers of particles interact, the overall behavior begins to show a preferred direction. Order slowly dissolves into disorder. Energy spreads outward. And the universe gradually moves towards states that allow more possible configurations. This perspective changes how we think about time itself. Instead of imagining time as a universal river carrying everything forward, physicists sometimes describe time as a property that emerges from deeper physical relationships. Something that arises when systems become large and complex enough. Something that reflects how information and energy flow through the universe. And when we explore the deepest levels of physical theory, we encounter hints that time might not be as fundamental as space itself. Some equations describing the universe treat time differently from the three familiar dimensions of space. Others suggest that time might emerge from more basic quantum processes. In certain approaches to quantum gravity, the universe can even be described by equations that do not contain time at all. Instead, time appears only when observers inside the universe begin measuring change. These ideas remain areas of active research. But they point toward a remarkable possibility. What we experience as the flow of time may not be a fundamental ingredient of reality. Instead, it may arise from deeper structures within spacetime. Structures that connect events across the universe in ways we are only beginning to understand. And when physicists follow this idea to its logical conclusion, they arrive at one of the most fascinating concepts in modern cosmology. The possibility that the entire history of the universe may already exist as a single structure. A structure where past, present, and future all coexist within the geometry of spacetime. In this view, time does not truly flow. Instead, we move through spacetime much like travelers moving through a landscape. Each moment is simply another location within that structure. This concept is known as the block universe. It is a way of thinking about reality that challenges our deepest intuitions about time. Because if the block universe is correct, then the distinction between past and future may not be as absolute as it appears. Both may already exist within the larger structure of spacetime. And the sensation of time flowing from one moment to the next may arise from the way conscious observers experience their journey through that structure. In the next part of our exploration, we will take a closer look at this remarkable idea. We will explore how Einstein's theory of relativity led physicists to consider the possibility that time might be another dimension of the universe. And how the entire history of the cosmos, from the birth of the first stars to the distant future of galaxies, might be woven together into a single, timeless structure within spacetime. In our everyday experience, time feels like a moving river. Moments appear to arrive one after another. The present seems to slide continuously forward, carrying us away from the past and toward the unknown future. Yesterday feels fixed. Tomorrow feels open. And the present moment appears to be the thin boundary between them. But when physicists began studying the nature of spacetime more deeply, they encountered an idea that challenges this familiar picture. According to Einstein's theory of relativity, space and time are not separate things. They are woven together into a single structure known as spacetime. Events in the universe are not simply located in space. They are located in spacetime, a four-dimensional structure consisting of 3 dimensions of space and 1 dimension of time. Every event has both a position and a moment, a location in space, and a location in time. Once physicists began thinking about the universe in this 4-dimensional way, a new perspective began to emerge. From this viewpoint, the universe can be imagined not as something that is constantly changing in time, but as a vast structure already containing all events within it. In this picture, the entire history of the universe exists as part of the geometry of spacetime. Past events exist in one region. Future events exist in another. And what we experience as the present is simply the moment our consciousness happens to be moving through. This idea is often called the block universe. Imagine spacetime as a vast landscape. In that landscape, every moment that has ever happened, and every moment that will ever happen, is represented somewhere within the structure. The birth of a star billions of years ago. The formation of Earth. The rise of civilizations. Even events far in the future that have not yet occurred from our perspective. All of these moments occupy different regions within the spacetime structure. From this perspective, the universe does not need to wait for the future to happen. The future may already exist as part of the spacetime landscape. Just as distant places already exist even if we have not yet traveled to them. To understand why this idea arises from relativity, we need to consider one of the most surprising consequences of Einstein's work. The relativity of simultaneity. Before Einstein, most people assumed that the present moment was the same everywhere in the universe. If something was happening now on Earth, then the same moment of now was also occurring on distant planets and stars. But relativity revealed that this intuition is not correct. The concept of the present depends on the observer's motion. Two observers moving relative to one another may disagree about whether two distant events happen at the same time. An event that appears simultaneous to one observer may occur earlier or later from the perspective of another. This difference arises because the speed of light is constant for all observers. Signals traveling through space take time to reach distant locations. As a result, observers moving in different ways slice spacetime into moments differently. This means there is no universal present shared across the entire universe. No single cosmic clock marking the same moment everywhere. Instead, each observer experiences their own sequence of events depending on how they move through spacetime. This insight led some physicists and philosophers to a striking conclusion. If there is no single universal present, then perhaps the distinction between past, present, and future is not fundamental. Instead, all events may exist together within the structure of spacetime. The present moment we experience may simply reflect our position within that structure. Just as a traveler moving across a landscape encounters different locations one after another. This view can feel deeply counterintuitive. After all, we experience the present moment as something special. The past feels fixed and unchangeable. The future feels uncertain and not yet real. Yet relativity suggests that the difference between these categories may arise from the perspective of observers moving through spacetime. From a broader view, the entire history of the universe may simply exist as a four-dimensional structure. A structure containing every event from the birth of the cosmos to its distant future. If this idea is correct, then time may not actually flow in the way we imagine. Instead, the flow of time may be something that emerges from how conscious beings experience their path through spacetime. Just as the sensation of movement arises when we travel through space. The universe itself may simply exist. Complete. A vast structure where every event has its place. In the next part of our journey, we will explore what this idea truly implies. Because if the block universe picture is correct, then the difference between past and future may be far less absolute than it appears. And the present moment, the moment we feel ourselves living in right now, may not be the universal boundary between what exists and what does not. Instead, it may be something far more personal. A perspective arising from the way our minds experience time within the larger structure of spacetime. To better understand the idea of a block universe, it can help to imagine something familiar. Think about a long road stretching across a quiet landscape. Along that road lie many places. A small town near the beginning. A forest further along. Perhaps a mountain pass somewhere in the distance. All of these locations exist at the same time, even if you have not yet traveled to them. As you move along the road, you experience each place one after another. First the town. Then the forest. Later the mountains. From your perspective, it feels as though the landscape is unfolding in front of you. But in reality, the landscape was already there. Your journey simply reveals different parts of it as you move forward. The block universe suggests that time may work in a similar way. The past, present, and future may all exist within the structure of spacetime. But conscious observers, beings like us, experience those moments sequentially as we move through that structure. Our awareness progresses from one moment to the next, giving us the sensation that time is flowing. Yet from a broader perspective, the events themselves may already exist within spacetime. This idea does not mean that the future is necessarily predictable. Even if all events exist within spacetime, observers within the universe may not possess the information needed to foresee what lies ahead. Just as someone traveling along a winding road cannot see beyond the next hill, we cannot see beyond the present moment. Our limited perspective creates the experience of uncertainty. But the structure of spacetime itself may still contain the full sequence of events. Another way to imagine this idea is through the pages of a book. When you read a novel, the story unfolds gradually. One page leads to the next. Characters face challenges, make decisions, and move toward outcomes that feel uncertain as the story progresses. Yet the entire story already exists within the book. Every chapter is already written. The beginning, middle, and ending all exist simultaneously within the physical object. The reader simply experiences those chapters sequentially. In the block universe picture, spacetime may be something like the pages of a cosmic story. Each moment occupies its own place within the structure. Observers living within that structure experience the story one moment at a time. But the full narrative may already exist across the geometry of spacetime. This concept may sound philosophical, but it arises naturally from the mathematics of relativity. When physicists describe the universe using spacetime diagrams, they treat time as another dimension alongside the three dimensions of space. Objects trace out paths through spacetime called world lines. A world line represents the history of an object. Every place it occupies across time. Your entire life can be represented as a single world line extending through spacetime. Your birth marks one point along that path. Your childhood, your memories, the moments you experience today. Each occupies a different location along that line. Future moments of your life would extend further along the same path. From the block universe perspective, that entire world line already exists within spacetime. What you experience as the present moment is simply the point along that world line where your awareness currently resides. This way of thinking about time challenges some of our deepest intuitions. We tend to imagine the past as fixed, the present as real, and the future as something that does not yet exist. But relativity suggests that these distinctions may arise from our perspective rather than from the fundamental structure of the universe. Different observers moving through spacetime may experience different sequences of events. Yet the underlying structure containing those events may remain unchanged. Some physicists describe this view as a timeless universe. Not because nothing changes, but because change itself is represented within the structure of spacetime. Every moment of change already occupies its place. This does not mean that our experience of time is an illusion. Our perception of time, the feeling of moving from one moment to the next, is a real and meaningful aspect of conscious experience. But it may arise from the way our minds process information as we move through spacetime. Our memories accumulate in one direction. We remember the past but not the future. Our brains construct a narrative that gives our experiences a sense of progression. And this progression creates the powerful sensation that time is flowing. Yet from the perspective of physics, the universe may simply exist as a complete spacetime structure. A structure where every moment has its place. Where the birth of stars billions of years ago and events billions of years in the future may both exist within the same cosmic framework. This idea can feel both unsettling and strangely peaceful. Because if every moment exists somewhere within spacetime, then the present moment we experience is simply one location within a much larger structure. A structure that includes everything that has ever happened. And everything that ever will. But the block universe raises another fascinating question. If past and future both exist within spacetime, why do we experience only one direction of time? Why does our awareness move steadily from earlier moments toward later ones? To explore that mystery, we must look again at the nature of entropy and the arrow of time. Because even within a universe where all moments exist together, the laws governing energy and disorder may still give our experience of time its familiar direction. And it is there, in the quiet increase of entropy across the cosmos, that we begin to see why the universe may allow time to feel as though it flows. Even if, at a deeper level, the structure of spacetime already contains the entire story. If the block universe idea is correct, it invites us to see reality in a very different way. Instead of imagining the universe as something that is constantly being created moment by moment, we might imagine it as a vast structure already containing the entire history of everything that exists. A four-dimensional landscape. Within that landscape lie the birth of stars, the quiet formation of planets, the rise of galaxies, and the countless small moments that shape the lives of living beings. Every event occupies its own place within the geometry of spacetime. From this perspective, time does not move. The universe simply is. Events do not come into existence and then disappear. Instead, they remain as part of the spacetime structure. Your childhood still exists as a region of spacetime. The distant past of the universe still exists somewhere within that cosmic structure. And future events may occupy other regions that we have not yet reached. This way of thinking can feel strange because our everyday experience suggests something very different. We feel ourselves moving through time. Memories accumulate behind us. The future appears open and uncertain. The present moment feels like the only part of reality that truly exists. But relativity suggests that this experience may arise from the way conscious observers perceive the universe rather than from the fundamental structure of reality itself. Our awareness moves along our world line, encountering different moments one after another. Just as a traveler moving across a landscape encounters different places along a path. The journey creates the experience of progression. But the landscape itself does not move. It simply exists. Some physicists describe this idea using a simple comparison. Imagine a film reel containing an entire movie. Every frame of the film already exists. The beginning of the story, the middle, and the ending are all present on the reel. But when the film is played through a projector, the frames appear sequentially on the screen. To the audience, the story unfolds moment by moment. Yet the entire sequence of events already exists within the film itself. The block universe suggests that spacetime may be something like that reel of film. Each moment of the universe is like a frame within the cosmic structure. Observers inside the universe experience those frames sequentially, giving rise to the sensation that time flows forward. Yet from a broader perspective, all of those frames exist together. This interpretation of space-time has been explored not only by physicists but also by philosophers trying to understand the deeper nature of time. Some thinkers find the block universe idea unsettling because it seems to challenge the concept of free will. If future events already exist within space-time, does that mean the future is fixed? Does it mean that our choices are somehow predetermined? These questions are still debated. Some physicists argue that the block universe simply describes the structure of space-time without necessarily determining how events unfold within it. Others suggest that the uncertainty built into quantum mechanics may still allow multiple possible futures to exist until events are resolved. For now, the relationship between space-time structure, quantum uncertainty, and human choice remains an open question. But even without resolving those philosophical debates, the block universe provides a powerful way of visualizing the cosmos. It reveals that time may not be an external force pushing the universe forward. Instead, time may simply be one dimension within the structure of space-time itself. A dimension through which events are arranged. A dimension that allows change to occur. And when we view the universe through that lens, something remarkable becomes clear. The distinction between past and future may not be as absolute as we once believed. Both may exist within the larger structure of space-time. Separated not by existence versus non-existence, but by our position within that structure. Yet the block universe does not solve every mystery about time. In fact, it raises even deeper questions. Because if space-time contains the entire history of the universe as a single structure, then what gives that structure its shape? Why does space-time exist at all? And at the deepest levels of physics, could space-time itself be something that emerges from an even more fundamental layer of reality? In recent years, physicists exploring theories of quantum gravity have begun to consider a surprising possibility: that space-time itself may not be fundamental. Instead, it may arise from deeper quantum relationships linking the building blocks of the universe. If that idea is correct, then both space and time may emerge from processes that operate at scales far smaller than atoms. Processes where the familiar concepts of distance and duration begin to lose their meaning. In those extreme regimes, the universe may behave in ways where time itself becomes uncertain, where the difference between earlier and later becomes blurred, and where the structure of space-time may dissolve into something far more subtle. To explore those possibilities, we must move beyond the large-scale structure of the cosmos and look deeper into the fundamental nature of reality. Because at the smallest scales of the universe, near the limits of quantum gravity, physicists suspect that time itself may begin to fade. And in those strange regions of reality, the familiar distinction between before and after may disappear entirely. For most of the history of science, time was treated as something simple. An invisible background. A steady rhythm ticking quietly beneath the events of the universe. Objects moved through space while time advanced steadily forward, like a cosmic clock counting the moments. Even after Einstein revealed that time could stretch and bend under the influence of gravity, time itself still seemed to exist as part of the structure of space-time. But as physicists began exploring the deepest layers of reality, they encountered an idea that seemed almost impossible to accept: the possibility that time itself might not be fundamental. That time, like temperature or pressure, might emerge from deeper processes rather than existing as a basic ingredient of the universe. This idea began to appear when physicists attempted to combine two of the most successful theories ever developed. On one side stood general relativity, Einstein's theory describing gravity and the curvature of space-time. On the other side stood quantum mechanics, the theory governing the behavior of particles and forces at the smallest scales. Each theory works extraordinarily well in its own domain. General relativity explains the motion of planets, the formation of black holes, and the expansion of the universe. Quantum mechanics explains the structure of atoms, the behavior of electrons, and the interactions of fundamental particles. But when scientists try to apply both theories at the same time, especially in extreme environments like the center of black holes or the earliest moments of the Big Bang, something strange happens. The mathematics becomes inconsistent. The equations refuse to cooperate. General relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics describes reality as a world of probabilities and discrete interactions. Trying to combine these pictures reveals deep tensions between them. To resolve this conflict, physicists have spent decades searching for a deeper theory known as quantum gravity. A theory that would describe how spacetime behaves at the smallest possible scales. And in this search, they have encountered something remarkable. In several approaches to quantum gravity, time does not appear as a fundamental variable at all. One of the most famous examples comes from an equation known as the Wheeler-DeWitt equation. This equation attempts to describe the quantum state of the entire universe. Unlike many equations in physics, it does not contain a variable representing time. Instead, the equation describes relationships between different possible configurations of the universe. From the perspective of this equation, the universe simply exists as a collection of possible states. There is no built-in clock marking the passage of time. At first glance, this idea seems deeply counterintuitive. After all, time appears to play a central role in every aspect of our experience. Events unfold. Processes evolve. Memories accumulate. Yet the Wheeler-DeWitt equation suggests that at the deepest level of reality, the universe may not require time in order to exist. Instead, time may arise only when observers inside the universe begin measuring changes between different states. In other words, time may emerge from relationships within the universe rather than existing independently. To understand this possibility, imagine a collection of photographs scattered across a table. Each photograph captures a different moment in a story. One shows a seed. Another shows a young tree. A third shows a tall forest growing years later. The photographs themselves do not contain time. They simply exist as images. But when we arrange them in a meaningful order, we begin to perceive the passage of time within the story they represent. Some physicists believe that the universe may behave in a similar way. The fundamental description of reality may consist of many possible states. Time emerges when observers interpret those states as sequences of change. This perspective suggests that time may not exist at the deepest level of physical law. Instead, time may appear when complex systems, including observers like ourselves, begin tracking how configurations of matter and energy change relative to one another. In this view, time becomes something relational. Something that emerges from patterns of change, rather than something that flows independently through the universe. If this idea is correct, then there may be regions of reality where the concept of time simply loses its meaning. Not because time stops, but because time was never fundamental to begin with. Near the Planck scale, the incredibly small distances where quantum gravity effects dominate, spacetime itself may break down into something more abstract. Distance may lose its familiar meaning, and duration may no longer exist as a separate dimension. Instead of space and time, the universe may consist of deeper quantum relationships linking different possible configurations of reality. Relationships that give rise to spacetime only at larger scales. This possibility opens the door to a fascinating conclusion. The universe we experience, with its flowing time and expanding space, may be only a large-scale approximation of a deeper underlying structure. At the deepest levels of physics, reality may be timeless. a network of relationships connecting different states of the universe. And time may emerge only when those relationships produce sequences that conscious observers interpret as past, present, and future. In the next part of our journey, we will explore how modern theories of quantum gravity attempt to describe this deeper layer of reality, and how those theories suggest that the familiar fabric of spacetime may arise from something far more fundamental, a hidden structure where the concept of time itself may not exist at all. If time may not exist at the deepest level of reality, the next natural question becomes almost impossible to ignore. What could the universe look like without time? It is difficult to imagine such a thing. Nearly every experience we have depends on time in some way. We wake up. We remember yesterday. We anticipate tomorrow. Even the language we use is built around the idea that events happen in sequence. One moment follows another. Cause leads to effect. But modern physics sometimes forces us to step outside the limits of our everyday intuition. And when physicists attempt to describe the universe at the smallest possible scales, the familiar structure of spacetime begins to dissolve. In several theories of quantum gravity, space and time themselves may emerge from something more fundamental. Something that does not resemble space or time at all. Instead of smooth spacetime, the universe may consist of extremely tiny building blocks connected by abstract relationships. One approach exploring this possibility is known as loop quantum gravity. In this theory, spacetime is not continuous. It is made of incredibly small units, woven together like threads in a cosmic fabric. These threads form networks sometimes called spin networks. Each node in the network represents a tiny quantum of space, and the links between them describe how these pieces connect. In this picture, space itself emerges from the relationships within the network. But time does not necessarily appear as a separate ingredient. Instead, change occurs through transformations within the network. Configurations shift from one arrangement to another. Observers inside the universe interpret these changes as the passage of time. But at the deepest level, the fundamental description may involve only relationships between different states. Another approach to quantum gravity comes from string theory. In this framework, the fundamental ingredients of reality are not particles but tiny vibrating strings. The different patterns of vibration give rise to the particles and forces we observe. String theory also suggests that spacetime itself may not be fundamental. Instead, spacetime may emerge from deeper mathematical structures governing how these strings interact. Some versions of the theory even suggest that the geometry of spacetime can arise from patterns of quantum entanglement. Entanglement is one of the strangest features of quantum mechanics. Two particles can become linked in such a way that measuring one instantly affects the state of the other, even if they are separated by enormous distances. When physicists began studying how large numbers of entangled particles behave together, they discovered something remarkable. The patterns of entanglement can resemble the geometry of spacetime itself. In certain models, the structure of space may arise from networks of entangled quantum states. If that idea is correct, then spacetime may not be the stage where physics happens. Instead, spacetime may be a consequence of deeper quantum relationships. A structure that emerges from the way information is connected throughout the universe. And if space emerges this way, time may emerge as well. Not as a fundamental dimension, but as something that appears when systems evolve through sequences of changing relationships. This perspective suggests that the familiar flow of time may only exist at larger scales. At the level where enormous numbers of particles interact and produce stable patterns. At the deepest scales of reality, those patterns may dissolve. And with them, the concept of time itself. To understand how radical this idea can be, imagine again those scattered photographs on a table. Each photograph represents a different configuration of the universe. One might correspond to an earlier arrangement of matter and energy. Another might represent a later one. But the photographs themselves exist outside of time. They simply exist. Time appears only when someone arranges the photographs into an ordered sequence. When an observer interprets the images as steps in a process. Some physicists believe the universe may behave in a similar way. The fundamental description of reality may consist of many possible states existing together. Observers interpret certain sequences of those states as the flow of time. But the deeper layer of reality may not contain time at all. Only relationships between states. This idea may sound abstract, but it helps resolve several puzzles in modern physics. For example, it offers a way to understand why time behaves differently in quantum mechanics and general relativity. If time emerges only at larger scales, then it is not surprising that the deepest equations of quantum gravity might not contain time as a basic variable. Instead, time appears only when complex systems begin measuring change relative to themselves. This concept also suggests that the universe may not be evolving in the way we imagine. Instead of reality constantly unfolding from moment to moment, the universe may consist of a vast landscape of possible states. Observers within that landscape experience change as they move through sequences of related configurations. And from that movement, the sensation of time emerges. But this still leaves one profound question. If time emerges from deeper quantum relationships, why does it appear so stable and consistent across the universe we observe? Why do clocks tick in such predictable ways? Why does entropy steadily increase? And why does the arrow of time seem so firmly established in the cosmos? To answer those questions, physicists look not only at the smallest scales of reality, but also at the enormous complexity of the universe as a whole. Because when vast numbers of particles interact across cosmic scales, new patterns begin to emerge. Patterns that make time appear steady, predictable, and universal. And it is within those patterns that the familiar flow of time returns. Even if, deep beneath the surface of reality, time itself may not truly exist at all. When physicists speak about a timeless universe, they are not suggesting that clocks will suddenly stop or that the world around us will freeze. Instead, they are pointing toward a deeper possibility. That time may not be one of the basic ingredients used to build reality. Rather, time may be something that appears only after the universe becomes large and complex enough for patterns of change to emerge. This idea is similar to the way other familiar concepts arise in physics. Temperature, for example, feels like a fundamental property of the world. We experience warmth and cold constantly. Yet temperature does not exist at the level of individual particles. A single atom does not possess temperature. Temperature appears only when enormous numbers of particles interact together. It is a collective property that emerges from motion. Some physicists believe that time may behave in a similar way. At the deepest level of reality, there may exist only relationships between different configurations of matter and energy. Those configurations do not necessarily occur before or after one another. They simply exist as possible states of the universe. Time emerges when observers compare those states and interpret them as sequences. In other words, time may be a way of describing change rather than a separate dimension through which change occurs. This perspective shifts the way we think about the universe. Instead of imagining reality as something constantly moving forward through time, we might imagine a vast landscape of possible configurations. Each configuration represents a different arrangement of matter, energy, and geometry. Some configurations contain galaxies and stars. Others contain the earliest moments after the Big Bang. Still others may represent states far in the future when the universe has expanded and cooled. Observers living within certain configurations perceive change by comparing one configuration with another. Their memories record previous states. Their measurements predict possible future ones. And through this process, the experience of time arises. Yet the deeper structure connecting those configurations may not contain time at all. Instead, it may consist of relationships, mathematical links connecting different states of the universe. Relationships that determine which configurations are possible and how they connect. In this view, the universe may resemble an enormous web of interconnected possibilities. Each point in that web represents a complete description of the cosmos at a particular configuration. Observers experience time when they move along paths within that web. Their journey from one configuration to another creates the sensation that time is passing. But the web itself simply exists. Complete. Timeless. This picture of reality is still highly speculative. Physicists are actively searching for evidence that might support or refute these ideas. Yet the possibility remains deeply intriguing, because it suggests that the familiar structure of spacetime, with its flowing time and expanding space, may not be the final layer of reality. Instead, spacetime itself may be something that emerges from deeper patterns within the universe. Patterns involving quantum information, entanglement, and fundamental relationships between physical states. If that idea proves correct, it would mean that the universe we experience is only an approximation of a deeper reality. A reality where the concepts of distance and duration may not exist in the way we understand them. But even if time is not fundamental, the universe we inhabit clearly behaves as though time flows. Stars age. Galaxies evolve. Living creatures grow older. And entropy continues to increase across the cosmos. At the scales we observe, time appears stable and reliable. It provides the structure that allows complex systems to exist. Planets orbit stars. Chemical reactions occur. Life evolves. Our experience of time may therefore arise from the enormous complexity of the universe itself. When vast numbers of particles interact across cosmic distances, patterns of change become stable enough to create the appearance of a flowing timeline. Clocks tick. Events follow one another. And observers experience the passage of moments. Yet beneath this familiar structure may lie a deeper reality where time has no independent existence. A layer of physics where only relationships remain. Where the universe is described not in terms of before and after, but in terms of connections between different possible states. And if we follow this idea far enough, it leads us to some of the most extreme regions of the cosmos. Places where spacetime itself becomes unstable. Where gravity grows so intense that the geometry of spacetime begins to tear and twist beyond recognition. In these regions, our usual understanding of time may fail completely. Near the centers of black holes. At the singularities predicted by general relativity. And perhaps even at the very beginning of the universe. There, the familiar structure of spacetime may collapse. And the difference between past and future may disappear entirely. In the next part of our journey, we will explore these extraordinary regions of the cosmos. Places where the laws of physics push spacetime to its limits. And where the meaning of time itself may begin to break apart. Throughout the universe, gravity quietly shapes the motion of planets, stars, and galaxies. It bends the paths of objects through spacetime, guiding them along invisible curves created by mass and energy. Most of the time, these gravitational effects are gentle. Planets orbit their stars. Stars drift through galaxies. Galaxies slowly dance around one another over billions of years. But in certain places, gravity grows so strong that it begins to push spacetime itself toward its limits. These places are among the most mysterious objects in the cosmos. Black holes. A black hole forms when an enormous amount of matter collapses into a region of space so dense that its gravitational pull becomes overwhelming. Often this process begins when a massive star reaches the end of its life. After burning its nuclear fuel for millions of years, the star can no longer support its own weight. Gravity takes over. The star collapses inward. And if enough mass remains after the explosion of a supernova, the collapse continues without stopping. The result is an object so dense that not even light can escape from its gravitational grip. Around every black hole lies a boundary known as the event horizon. This boundary marks the point beyond which escape becomes impossible. Anything crossing the event horizon, matter, radiation, even light itself, can no longer return to the outside universe. From the perspective of a distant observer, the event horizon appears as a dark surface surrounding the black hole. Yet this boundary is not a physical wall. Nothing special happens at that exact location for an observer falling inward. But the geometry of spacetime changes dramatically once the horizon is crossed. Outside the event horizon, objects can still choose their paths through spacetime. They can move away from the black hole if they have enough energy. Inside the event horizon, the structure of spacetime changes in a profound way. All possible paths lead inward. Just as every path on Earth eventually leads toward the center when you are falling through the sky, every path inside a black hole leads toward the central singularity. And this is where time itself begins to behave in ways that challenge our deepest intuitions. To understand what happens near a black hole, we must first consider one of the most fascinating predictions of general relativity: gravitational time dilation. According to Einstein's theory, gravity does more than pull objects together. It also affects the rate at which time passes. Clocks located in stronger gravitational fields tick more slowly than clocks in weaker ones. This effect has been measured many times. Even on Earth, clocks placed at slightly different altitudes run at slightly different speeds. A clock on a mountain runs a tiny bit faster than a clock at sea level. The difference is incredibly small, but it can be measured with precise instruments. Near a black hole, this effect becomes far more dramatic. As an object approaches the event horizon, the gravitational field grows extremely intense. To a distant observer watching from far away, time near the black hole appears to slow down. A clock carried by someone falling toward the event horizon would appear to tick more and more slowly. Signals sent outward from the falling observer would take longer and longer to arrive. The light they emit would become increasingly stretched and redshifted. Eventually, to the distant observer, the falling traveler would appear to freeze near the edge of the event horizon. Their clock would seem to slow almost to a stop. Their image would fade and dim as the light escaping from them becomes weaker and weaker. From the outside perspective, it would look as though the traveler never quite crosses the event horizon at all. Instead, they would appear to linger near the edge indefinitely. Yet this is only how the situation appears from far away. For the traveler falling toward the black hole, the experience would be very different. Their own clock would continue ticking normally. They would not feel time slowing. From their perspective, they would cross the event horizon after a finite amount of time. Nothing dramatic would happen at the exact moment of crossing. There would be no visible boundary. No sudden barrier. They would simply continue falling deeper into the gravitational well. This difference in perspectives reveals something profound about spacetime near a black hole. Time itself behaves differently depending on where you are and how you move. Observers in different locations experience different flows of time. And as one approaches the event horizon, the familiar structure of time begins to stretch in extraordinary ways. But the event horizon is only the beginning of the story. Because deeper inside the black hole lies a region where gravity becomes so intense that the known laws of physics begin to break down. A region known as the singularity. According to the equations of general relativity, the singularity represents a point where density becomes infinite and spacetime curvature becomes extreme beyond measure. And near this mysterious region, the distinction between space and time may collapse entirely. In the next part of our exploration, we will venture deeper into the strange interior of black holes. And we will discover how the structure of spacetime itself may twist in ways that erase the familiar difference between past and future. Once an object passes the event horizon of a black hole, the nature of spacetime begins to change in ways that are difficult to imagine. Outside the horizon, space and time behave in the familiar way we experience every day. Time moves forward. Space offers directions we can travel. We can choose to move north or south, east or west. We can move upward or downward. And although we cannot move backward in time, we are free to move through space in many directions. But inside a black hole, according to the mathematics of general relativity, something remarkable happens. The roles of space and time begin to shift. Outside the event horizon, moving toward the center of the black hole is a choice. A spaceship could, in principle, fire its engines and escape if it stays far enough away. But once the horizon is crossed, moving toward the center becomes unavoidable. No matter what direction an object tries to move, every possible path leads deeper inward. In a sense, the direction toward the singularity becomes as inevitable as the future itself. To understand this strange situation, imagine the way we normally experience time. No matter what we do, we cannot stop time from advancing. We cannot choose to remain frozen in the present moment forever. Every second carries us forward. The future approaches whether we wanted to or not. Inside a black hole, the direction toward the singularity behaves in a similar way. Just as we cannot avoid moving into the future, anything inside the event horizon cannot avoid moving toward the singularity. All possible trajectories lead there. This strange behavior arises because spacetime becomes so severely curved that the usual distinction between spatial directions and the direction of time begins to blur. In certain descriptions of black hole interiors, the radial direction, the direction pointing toward the center, begins to behave like a time dimension. And the dimension that previously represented time begins to behave more like a spatial coordinate. This does not mean that time literally turns into space. But mathematically, the structure of spacetime rearranges itself in a way that makes the inward direction unavoidable. Just as moving into the future cannot be prevented. This leads to a profound conclusion. Once something crosses the event horizon, reaching the singularity is not merely likely. It is inevitable. The singularity lies in the future of every object inside the black hole. No amount of effort, no rocket engine, no clever maneuver can prevent that outcome. Just as no one can avoid moving forward through time. The journey toward the singularity becomes the future that awaits everything inside. For the traveler falling inward, this journey would occur in a finite amount of time. Depending on the size of the black hole, the trip from the event horizon to the singularity might take only seconds or minutes. For extremely large black holes, the kind found in the centers of galaxies, the journey might last longer. But eventually, according to classical general relativity, the traveler would reach the singularity. And it is here that the known laws of physics begin to fail. The equations describing spacetime predict that curvature becomes infinite. Density grows without limit. And the structure of spacetime itself collapses into something we do not yet understand. Physicists believe that this prediction signals the breakdown of general relativity. A more complete theory of quantum gravity would likely replace the singularity with a new description of spacetime at extremely small scales. Yet even before reaching the singularity, the environment inside a black hole becomes extraordinarily strange. Tidal forces grow immense. Gravity pulls more strongly on the part of your body closer to the black hole than on the part farther away. This stretching effect is sometimes called spaghettification. Objects falling into smaller black holes would be torn apart by these tidal forces long before reaching the center. But in extremely large black holes, the tidal forces near the event horizon may actually be relatively gentle. An observer might cross the horizon without immediately noticing anything unusual. The most dramatic effects would occur deeper inside. Yet regardless of the details of the journey, the deeper truth remains. Inside a black hole, the familiar structure of time begins to unravel. The distinction between space and time becomes blurred. The future is no longer something distant. It becomes a direction pointing inward, toward a region where the geometry of space-time may collapse completely. And this strange environment leads to some of the most fascinating questions in modern physics. What truly happens at the singularity? Does space-time tear apart completely? Does a deeper layer of quantum gravity take over? Or could the interior of a black hole connect to other regions of spacetime entirely? Some theories even suggest that black holes might act as bridges to other parts of the universe. Or perhaps to entirely different universes. For now, these possibilities remain speculative. Yet they remind us that black holes represent more than just gravitational traps. They are natural laboratories where the limits of spacetime are pushed to their extremes. Places where our understanding of time itself may begin to fail. And where the boundary between past and future may dissolve into something far stranger than we ever imagined. In the final part of our journey, we will explore what these extreme environments might reveal about the ultimate fate of time in the universe. And whether the cosmos itself may one day reach a state where the distinction between before and after fades away entirely. Black holes are often described as the most extreme objects in the universe. Regions where gravity grows so powerful that the familiar rules of space and time begin to bend in extraordinary ways. Yet the deeper scientists study these objects, the clearer it becomes that black holes may represent something even more profound. They may be places where our understanding of time itself begins to fail. Outside a black hole, time behaves in ways that, although sometimes strange, still follow the predictions of relativity. Clocks tick more slowly near massive objects. Signals become stretched by gravitational redshift. Observers moving in different ways may disagree about the order of certain events. But the basic structure of spacetime still exists. Events happen. Processes unfold. The future continues to arrive. Inside a black hole, however, the structure of spacetime becomes far more unstable. As one moves closer to the central singularity, the curvature of spacetime grows increasingly intense. The equations of general relativity predict that this curvature eventually becomes infinite. But infinities in physics often signal something important. They usually indicate that the theory being used has reached the limits of its validity. General relativity is incredibly successful at describing gravity across vast cosmic distances. It explains the motion of planets, the behavior of galaxies, and the expansion of the universe itself. Yet the theory was never designed to describe what happens at infinitely small scales. Near the singularity of a black hole, spacetime may be compressed to such an extreme degree that quantum effects become unavoidable. At that point, the smooth fabric of spacetime predicted by relativity may no longer exist. Instead, spacetime may become turbulent, fluctuating, and uncertain. Some physicists imagine this region as a kind of quantum foam, where the geometry of spacetime constantly shifts and rearranges itself. Distances may fluctuate. Durations may become uncertain. And the familiar concept of a smooth timeline may break apart. In such a regime, the idea of a well-defined before and after may no longer apply. Events may not occur in a clear sequence. Instead, the structure of spacetime itself may dissolve into a deeper quantum description of reality. What that description looks like remains one of the greatest mysteries in modern physics. Several competing theories attempt to describe what might replace the singularity. Some approaches suggest that quantum gravity may prevent true infinities from forming. Instead of collapsing to an infinitely dense point, matter might reach an extremely dense but finite state. Others propose that the interior of a black hole might bounce outward, potentially forming a new region of spacetime. In some speculative models, black holes could even give birth to entirely new universes. Each black hole might become the seed of a new cosmos expanding somewhere beyond our observable universe. These ideas remain highly theoretical, but they illustrate how black holes force physicists to confront the deepest questions about the nature of time and space. Because if spacetime itself can collapse inside a black hole, then time may not be an absolute feature of reality. It may exist only in certain regions of the universe where spacetime remains stable. And in other regions, such as near singularities, the familiar structure of time may disappear entirely. Black holes may therefore represent boundaries in our understanding of reality. They show us that the universe can reach conditions where the known laws of physics no longer provide clear answers, where space and time blur together, and where the distinction between past and future may lose its meaning. Yet black holes are not the only places where time may face such limits. There is another moment in the history of the universe where the structure of spacetime may have broken down completely. A moment that lies far deeper in the past than any black hole. The very beginning of the cosmos. The moment we call the Big Bang. According to our current theories, the universe began about 13.8 billion years ago in an extremely hot and dense state. As we trace the expansion of the universe backward in time, the density of matter and energy grows ever larger. Eventually, the equations of general relativity again predict a singularity. A point where spacetime curvature becomes infinite and the known laws of physics break down. But just as with black holes, many physicists believe that this prediction does not represent a true physical singularity. Instead, it may mark the boundary where our current theories cease to apply. Beyond that boundary may lie a deeper description of the universe, one where spacetime itself emerges from more fundamental quantum processes. If that is the case, then the Big Bang may not represent the beginning of time. Instead, it may mark the point where time itself began to emerge from a deeper timeless structure. In other words, time may not have existed before the Big Bang. Not because it stopped, but because the concept of time itself had not yet formed. And this possibility leads us to one final, extraordinary question. If time emerged at the beginning of the universe, could it one day disappear again? Could the distant future of the cosmos reach a state where the distinction between past and future slowly fades away? And could the universe itself eventually enter a phase where the concept of time no longer applies? In the final part of our exploration, we will consider the ultimate fate of time in the cosmos, and what the long future of the universe might reveal about the deepest nature of reality itself. When we look out into the night sky, we are not only seeing distant places, we are also looking into the past. The light from distant galaxies travels for millions, sometimes billions of years before reaching our eyes. In a sense, every telescope becomes a time machine. By observing distant regions of space, we can glimpse earlier chapters in the history of the universe. Over the past century, astronomers have used these observations to reconstruct an extraordinary story. A story about how the universe began. In the early 20th century, scientists discovered that distant galaxies are moving away from us. The farther away a galaxy is, the faster it appears to be receding. This observation revealed something profound. Space itself is expanding. Galaxies are not simply flying outward through empty space. Instead, the fabric of spacetime itself is stretching. As the universe expands, the distances between galaxies gradually grow larger. If we imagine reversing this expansion and tracing the motion of galaxies backward through time, something remarkable happens. The universe becomes smaller. Galaxies move closer together. Matter and radiation grow increasingly dense. Eventually, all the matter and energy in the observable universe converge into an extremely hot, compact state. This early phase of the universe is what we call the Big Bang. The Big Bang was not an explosion in space. It was an expansion of space itself. In the earliest moments after this event, the universe was incredibly hot and dense. Particles moved with enormous energy. Light could not travel freely because matter was packed so tightly together. As the universe expanded and cooled, matter began to organize into more stable forms. Quarks combined to form protons and neutrons. Atomic nuclei began to form. Hundreds of thousands of years later, electrons joined these nuclei to create the first atoms. With the formation of atoms, light was finally able to travel freely through space. Some of that ancient light still fills the universe today. It is known as the cosmic microwave background. This faint glow, detected by radio telescopes, represents the oldest light we can observe. It carries with it a snapshot of the universe when it was only about 380,000 years old. By studying this radiation, scientists have learned an enormous amount about the early universe. They have measured its age, its composition, and the tiny fluctuations that eventually grew into galaxies and clusters of galaxies. Yet even with all this knowledge, one profound mystery remains. What happened at the very beginning? When physicists use general relativity to trace the expansion of the universe backward in time, the equations eventually lead to a singularity. A moment when density becomes infinite and the curvature of spacetime becomes extreme beyond measure. In classical general relativity, this singularity appears to mark the beginning of time itself. Before that moment, the equations no longer describe a meaningful universe. In this sense, time itself appears to start at the Big Bang. Just as there is no point north of the North Pole on Earth, there may be no moment earlier than the beginning of time. The question, what happened before the Big Bang, may not have a meaningful answer if time itself did not yet exist. Yet many physicists suspect that this picture is incomplete. Just as singularities appear inside black holes when our theories reach their limits, the Big Bang singularity may indicate the breakdown of general relativity rather than a true beginning. A deeper theory of quantum gravity may reveal what happened in those earliest moments. And some of the ideas proposed by physicists are astonishing. In certain models of quantum cosmology, the Big Bang may not represent the beginning of the universe. Instead, it could represent a transition. A phase where the universe changed from one state to another. Some theories suggest that the universe may have existed in a different form before the Big Bang. Perhaps as a contracting cosmos that eventually rebounded into expansion. Other theories imagine that our universe may have emerged from a larger cosmic landscape. One universe forming within a vast multiverse. There are even proposals suggesting that time itself might emerge gradually as the universe evolves. In these scenarios, the earliest moments of the cosmos may not have contained time in the way we experience it today. Instead, time may have crystallized from deeper quantum processes as the universe expanded and cooled. If that is true, then time may not be a permanent feature of reality. It may be something that appears only under certain conditions. Conditions that allow the universe to develop stable structures, growing entropy, and observers capable of experiencing change. And if time can emerge under certain conditions, it may also be possible for time to disappear again. In the next part of our journey, we will explore how the far future of the universe might transform the nature of time itself, and whether the ultimate fate of the cosmos could lead to a state where the distinction between before and after slowly fades away. If time may have emerged along with the birth of the universe, it is natural to wonder what might happen in the distant future. Will time continue flowing forever? Or could the cosmos eventually reach a state where the distinction between past and future begins to fade away? To explore this question, physicists often look at one of the most fundamental principles in nature: the steady growth of entropy. As we discussed earlier, entropy measures the number of ways a system can be arranged. Highly ordered systems have low entropy. Disordered systems have high entropy. Across the universe, physical processes tend to move toward states of higher entropy. Energy spreads outward. Structures gradually break down. And over vast spans of time, order slowly gives way to disorder. This tendency gives rise to what we call the arrow of time. It is the reason we remember the past but not the future. The reason broken glass does not spontaneously reassemble itself. The reason stars burn their fuel and eventually fade. Entropy increases not because the laws of physics demand it absolutely, but because higher entropy states are vastly more probable. There are simply more ways for the universe to be disordered than ordered. Over cosmic timescales, this statistical tendency shapes the evolution of everything. Stars form from collapsing clouds of gas. They shine for millions or billions of years. Eventually, their nuclear fuel runs out. Some stars collapse into white dwarfs. Others explode as supernovae. The most massive stars leave behind neutron stars or black holes. Galaxies continue evolving as stars form and die. But this process cannot continue forever. The universe contains a finite supply of usable energy. And as entropy grows, that energy becomes increasingly spread out. Over extremely long timescales, far beyond the current age of the universe, the cosmos may approach a state known as heat death. In this scenario, stars have long since burned out. Black holes slowly evaporate through a process known as Hawking radiation. Galaxies drift farther apart as cosmic expansion continues. Eventually, the universe becomes an enormous, dark expanse containing mostly cold particles and faint radiation. Temperature differences disappear. Energy becomes evenly distributed. And without energy gradients to drive physical processes, very little change continues to occur. At this stage, the universe may enter a state of near thermodynamic equilibrium. Nothing dramatic happens. No new stars ignite. No complex structures emerge. Only an immense, quiet stillness remains. And in such a universe, the concept of time may begin to lose its meaning. After all, time is closely tied to change. We measure time by observing processes. The ticking of clocks. The motion of planets. The vibrations of atoms. But in a universe where almost nothing changes, there may be no reliable processes left to mark the passage of time. Imagine a universe where every particle drifts slowly through an almost perfectly uniform sea of radiation. Where temperatures are nearly identical everywhere. Where interactions between particles occur only rarely across unimaginable distances. In such a cosmos, the arrow of time becomes extremely faint. Entropy has already reached its maximum. There is little left to increase. And without increasing entropy, the direction of time becomes difficult to define. From the perspective of physics, time may still exist as part of the structure of spacetime. But without meaningful change, the difference between earlier and later moments may become almost impossible to detect. The universe would not freeze completely. Random fluctuations would still occur. Particles might occasionally collide. Quantum processes would continue at microscopic scales. But on large scales, the cosmos would appear almost static, an immense expanse of quiet darkness stretching across trillions upon trillions of years. Some physicists have suggested that in such a universe, the concept of time might slowly dissolve into irrelevance. Without processes that produce new structures or increasing entropy, there would be no meaningful arrow pointing from past to future. The universe would simply exist in a state of near-perfect equilibrium. Yet even this quiet ending may not represent the final chapter of the story. Because some theories of cosmology suggest that even in a nearly empty universe, rare fluctuations might still occur. Given enough time, vast stretches of time beyond ordinary comprehension, random quantum fluctuations could occasionally produce small pockets of lower entropy. Tiny regions where new processes begin again. These fluctuations would be extraordinarily rare. But in a universe lasting long enough, even extremely unlikely events might eventually occur. And such possibilities remind us that the ultimate fate of time in the cosmos remains uncertain. The universe may approach stillness. Or it may contain hidden processes that eventually create new beginnings. To understand what these possibilities might mean, we must step back and consider one final question. Not just how time began. And not just how time might fade. But whether time itself may be only one chapter in a much deeper story about the nature of reality. And that question leads us to the final reflection of our journey. As we step back from the many ideas we have explored, a quiet realization begins to take shape. Time, which feels so simple in our daily lives, may be far more mysterious than we ever imagined. We wake each morning and feel that time moves forward. Moments pass. Memories accumulate. The past becomes fixed, while the future remains unknown. This experience feels so natural that it is easy to assume time itself must be one of the most basic features of the universe. Yet when physicists examine the deepest laws of nature, a different picture begins to emerge. Time can slow. Time can stretch. Time can pass at different rates depending on gravity and motion. Near black holes, the structure of time begins to warp in extraordinary ways. In quantum theory, the most fundamental equations sometimes appear to work without time at all. And at the beginning of the universe, the very concept of time may have emerged from deeper processes that we are only beginning to understand. These discoveries suggest something remarkable. Time may not be the foundation of reality. Instead, time may be something that arises from the relationships between events. Something that emerges when the universe becomes complex enough for change to occur. From our perspective inside the cosmos, time feels like a flowing river carrying everything from past toward future. But from a deeper viewpoint, the universe may simply exist as a vast structure of events connected across space-time. A structure where the distinction between past and future depends on how observers move through that landscape. In this sense, time may be less like a river and more like a dimension of a vast cosmic map. A dimension that allows events to be arranged and experienced in sequence. Yet even this picture may not represent the final layer of reality. At the smallest scales of the universe, spacetime itself may dissolve into something more fundamental. Quantum relationships. Networks of information. Patterns of entanglement linking different states of the cosmos. Within that deeper layer, the familiar ideas of space and time may no longer apply. Instead of distances and durations, reality may consist of connections between possible configurations of the universe. Time emerges only when those configurations are experienced as sequences of change. And when the universe grows large and complex enough, the arrow of time appears. Entropy increases. Stars form and burn. Galaxies evolve. Life emerges. And conscious observers begin asking questions about the nature of time itself. Yet far in the future, the cosmos may once again approach a quieter state. Stars will fade. Black holes will slowly evaporate. Energy will spread thinly across an ever-expanding universe. In that distant era, the processes that define the arrow of time may grow weaker. Change may slow. And the universe may drift toward a state where the distinction between earlier and later becomes increasingly subtle. If that happens, time may not end in a dramatic moment. Instead, it may slowly fade into the background of reality, still present in the structure of spacetime, yet no longer shaping the universe in the way it once did. But even then, the deepest questions about time may remain open. Because every answer we discover about the cosmos seems to reveal an even deeper mystery beneath it. Does time truly exist as a fundamental dimension? Or is it something that emerges from deeper physical laws? Did time begin with the birth of the universe? Or did the universe emerge from a timeless reality beyond our current understanding? These questions remind us that the universe is still far more mysterious than we can fully comprehend. Yet the search for answers continues. Every telescope pointed toward distant galaxies. Every experiment probing the quantum world. Every equation describing the geometry of space-time brings us a little closer to understanding the nature of reality. And perhaps one day, physicists will uncover the deeper structure from which space, time, and the entire universe emerge. Until then, the mystery of time remains one of the most fascinating puzzles in science. A quiet reminder that even something as familiar as the passing of moments may hold secrets stretching across the entire cosmos. And as we look up at the night sky, watching the slow motion of stars and galaxies across the universe, we are also witnessing the passage of time itself. A journey that began billions of years ago. And that may continue, in one form or another, far beyond the limits of our imagination.